Good morning and welcome all. My staff members are industry expert, Mr. Kapil Bhudhia from Klingenberg, participants of Institute for Advanced Computing and Software Development, popularly known as IACSD and ETC of CDAC Acts, and students from DYPIET Pimpri College. So we welcome you once again and good morning. You are aware that Institute for Advanced Computing and Software Development, which is a premier training institute and a finishing school, nurturing and grooming students from last 23 years in the field of IT. We have three flagship courses: Diploma in Advanced Computing, Diploma in Big Data Analytics, Diploma in IT Infrastructure, Systems and Security. We also have a preparatory course for the CCAT examination. We also conduct some of the modular and certification courses. All the courses except for the preparatory course are linked with the placement assistance, 100% placement assistance. To all, probably you are aware, and since you have joined, you are aware that IACSD has been maintaining very high quality of education, and in order to provide you something extra apart from what the regular education is, regular training is, we always conduct such kind of industry expert sessions wherein the industry person comes and engages you and shares what happens in the real world, and you get a knowledge, a know-how, and a brief idea how you should proceed ahead once you join your professional life. Okay. Just a So, and to say something about Mr. Kapil, he is the head of the Pune software division of Klingenberg actually, and he is an alumni of CDAC. More about his journey and something about him, he'll only be explaining. My colleagues are there, Mr. Rohit, Mr. Karan, Mrs. Vaishali, and if somebody else is over there, they're all welcome. And I welcome Mr. Kapil and hand over the proceedings to him. He will guide you, and I hope all of you will have multiple things to take away from this session. This should be really a session wherein you would know, you would learn how to develop algorithms and how to decode the data structures. Over to you, Mr. Kapil.
Hello. Am I audible?
Yeah, audible, clear.
Perfect. Thank you. So thanks for that nice introduction, Mr. Keshav. I appreciate that. So to start with, I would probably not spend a whole lot of time, but maybe briefly go over introducing myself. So hello and good morning to everyone here. I don't know how many students have participated today. How many people in the meeting?
268.
268. That's great. That's a nice Sunday morning. Not the best atmosphere, not the best climate, but it's amazing to be among 268 people and to be doing this session. So I really thank you, Mr. Keshav and the team, to sort of give me this opportunity. Brief introduction about me. So I have, I'm not an engineer like most of you are. So I did not do engineering. I'm a graduate in maths from Bombay University. And then I went on to do my master's in computer science, again from Bombay University. Meanwhile, while I was doing that, I did a course on PGDST. At that time, it was called NCST. This was my introduction to computers. And I still remember how scared I was when they finished a C in the first 2 months with 3 hours session on a Saturday. And looking at all those pointers in the shared text, I was going crazy. I had only seen math symbols up to that point, and arrows was a bit new to me. But the journey has been really exciting so far. So I went on to do my master's in information technology from IIT Mumbai. After that, I finished the NCST course. We were only 10 of us who could finish that. And then I worked with ANSYS in 2004. I came to Pune. I started working with a company called ANSYS. Back then it was called Fluent, and they were into computational fluid dynamics. So I was basically tasked with improving runtimes of the algorithms, because what Fluent was doing, we were solving real physics problems, in the sense, simulating them, which basically means that you have to create millions of cells in your program, and then run some equations on those miniature cells, and these are millions of them. Which means your algorithms have to be really, really good, because even if you lose a microsecond or a second somewhere, that's a huge time. Yeah, if you multiply that by a million. So I sort of enjoyed the journey. I worked with Fluent for about 6 years. I worked on a lot of optimization problems, high computing problems. And it was a really exciting journey. I then moved on to another company called Renishaw. They were into the metrology domain. And there I was tasked with creating algorithms for measuring real physical parts. And this was challenging in the sense, we have to drive a machine, and the machine has to touch the parts at specific points, make sure it does not crash into the part. So I have to do collision detection, I have to do path planning. So it was, again, also a very, very interesting journey. With Renishaw, I was working from their headquarters in Newmilns in Gloucestershire, UK. And then I came here back in India in 2017, and I joined Klingenberg as the development head. So I've been handling this position at Klingenberg. We've been working on very cutting edge stuff. So I have sort of moved away a bit from algorithms now. I am looking at developing microservices for the manufacturing shop floors. So we are into IoT, and we are doing some cutting edge industry 4.0 stuff, including things like OPC UA. We have products which are deployed in the cloud. We do all our DevOps is based on Azure platform. So that's a very different thing than where I started my journey. But things have been amazing so far. Yeah. So again, a very warm welcome to every one of you, and thanks for joining. So we'll start with the session now. One of the things I really ask of you is to be alert. Yeah, and I would really like participation, because algorithms is not something where it can be a one-way interaction. Yeah, I would really, I would be asking questions in between, and I would really be expecting some good participation from your end. So please speak up, don't be shy. I can't see your face, and it doesn't matter. Yeah, so please speak up. And let's make the session really interactive. So if you're not following something, or you think I'm going too fast, please let me know, and then I'll try and make some changes. Yeah. So thanks, and let's get started. So I'm going to share my screen now.
And I update now. There are somewhere 300 students.
Okay, this gets it's getting interesting. Okay, so how do I go about sharing my screen?
Rohit, give the rights.
Sir has the rights.
Okay, perfect. Thank you, Rohit. And okay, share screen. Screen 1, screen 2. So can you see my screen?
Yes, sir.
Yes.
Okay, right. So what do you see? Dolphins?
True.
Yeah, I would like the students to say something.
Sorry. They'll. I just thought that you were checking that.
Yeah, so I just, so I would appreciate if the students now speak up, yeah. So what does everyone see? Do they see dolphins or they see some interesting algorithmic stuff? Keshav, you tell me there are 300 students out there.
You can unmute and then speak. They're
Dolphin,
putting in the chat.
dolphins.
Dolphins. Yes, okay, perfect. So I know at least there are two people out there, Keshav. Okay, great. So, but I believe this is not what we want to discuss, right? We don't want to discuss dolphins and interesting animal facts. Yeah. So this is my son was trying to teach me some animal facts. But what we are going to do is something probably more interesting. Yeah. What I want to do today is I'm going to, so I've done these sessions in the past, and Mr. Keshav asked me to sort of, turn on the gears and go a bit higher level. He thinks the students, this batch are really amazing, and they can cope up with something more advanced. So I decided to talk about heat. Yes. And I would like to understand if this data structure has been done with you before. If you're not speaking, I would advise please mute yourself. Otherwise there can be sounds in the background which can disturb the entire class. So I would really appreciate if you mute yourself while you're not talking. Yeah. Okay. So have you all done heat before?
Yes, sir, little bit.
Little bit. So what is meant by little bit? Like you heard the word heap.
No, sir, just know the concept that the top of minip and maxip.
Okay. Okay. Right. So let me see if I can. Is there a way to move this? Yes. Sorry, say that again. Okay. So I'm going to share some sort of a whiteboard. And, yes, I said it now. Just be patient with me. Perfect. That's good. So now we need some shapes. Not this one. Shapes. Okay. So we're talking of heaps. A heap is basically maintained as a binary tree. I'm hoping everyone knows what a binary tree is. The different, when we say binary, it basically means that everyone. I hope everyone knows what a tree data structure is, right? So you have the concept of a root, and then you have nodes below that root. Yeah, something like this. Yeah. Right, and then there's concept of like complete binary trees where every node has a, except for the leaf nodes, every node has a child. Okay, so a heap is maintained. If you don't understand something, please point it out. Yeah, so a heap is maintained as a binary tree. Yeah? And in this case, it's like a, it's not necessarily a complete binary tree, but you will not find gaps except for at the leaf nodes. Yeah. So in this case, for example, you would have every time. A painful job. Okay, perfect. Finally. Now, we have two kinds of heap. There's a max heap and there's a min heap. Yeah, we'll talk about the max heap. The concept, the idea of a heap is that when we say it's a max heap, then you look at, so in a tree structure, you can see that there are many subtrees. Yeah, so you have a tree starting at the very root node, and then you have these subtrees. If you sort of notice, this is freehand, right? So this is a left subtree, and this is a right subtree for this particular root node. Yeah. Similarly, for this, if I imagine this as the root node, then this is its left subtree, and this is its right subtree. And similarly, for this root node, there is left subtree and right subtree. Yeah. Now, the thing to notice is, that every node can be treated as a root node. I mean, for example, in this case, if I treat this as a root node, then in this case, in this specific leaf node case, there is no right subtree or a left subtree. Yeah. The property of the heap is, for example, let's talk about max heap. So we talk about max heap. Okay, so max heap is where the maximum element for every subtree is at the root node. Yeah, and this property is not only satisfied at the root node, but is satisfied at every subtree of that entire tree. Yeah, which by that, what do I mean? So for example, one of the valid max heap could be something like, say, 56 here, and 67 here, and then 14 here, $34, 97, 2, 45, let's say, and okay. So how many of you think this is a valid max heap? Can somebody answer that? How do I see the participants at the same time?
No, sir, it is not max heap.
max heap. May I know your name so I know who's talking?
Kedar.
Kedar. So Kedar, why do you think this is not a max heap?
So in max heap, the topmost element, so the topmost element should be the largest element, and below that the smallest elements are placed.
Okay.
So 97 should be placed at the top, and then smaller, then again smaller than the root node. You have to place every time.
Okay, fine. So you're saying 97 should have actually been here rather than
Yes.
56, right?
Yes.
Yeah, that's correct. So we bring it here.
Still
Is
it
it
is
a
not.
max?
No, sir. Still it is not. You have to
Still it is
place
not.
every child node should be lesser than the parent node. That's the conception.
Right, right. So because we just satisfied the max heap property at the root node, it is still not the entire structure, the entire data structure is still not max heap. Yeah. Now, if you want to sort of actually convert this into max heap, then we have to understand an algorithm which can basically go over, because clearly it's not the way that I look at a certain element and then I swap it with one random element, right? I need to ensure that the entire data structure is satisfying the max heap property. Yeah. So the way to start that is, we basically start at the leaf nodes, okay, and we look at its parent. Yeah. So in this case, we are looking at 34, okay, and then we look at all the childs of that parent. So in this case, 34 has no other child than 55. Yeah. And we look at that and we say, is it satisfying the max heap property? Yeah. Is it satisfying the max heap property in this case? Somebody other than Kedar?
No, sir.
No. Right? Why is that? Because clearly, if I look at just this subtree, so this is the one that I'm currently focusing on, and I look at that and I say clearly 55 is greater than 34, and by the max heap property, 55 should have actually been at the root position, which is not the case. Here. So what that means is I'm basically going to swap their positions. Yeah. Right. So I swap their positions. So 55 comes here and 34 goes there. Okay. And then the next thing I do is I come to the node. So this was the last node in the tree. And then I come to the second last node and I sort of keep going like that. Yeah. So imagine, these are sort of in an array. Yeah. And it's difficult to draw the array here, but let's imagine the array looks something like this. Okay. Okay, so the array looks something like 97, 67, 14, 55, 56, 2, 5, and 34. Yes, and these are at positions. So they are position 0, 1, 2, 3, 4, 5, 6, 7, 8. Right, so I hope you get it. 3, 4, 5, 6, 7. Did I miss something here? 2. 1, 2, 3, 4, 5, 6, 7, 8, 8. Yeah. So if you notice, the elements would be arranged in a simple array like that in this fashion, and we want to sort of make sure that this array satisfies the max heap property. Yeah. So we treated 34 Okay, and we sort of swapped its position with 55. So we had 55 at the bottom, and we swapped its position to 34. The next element that we're going to treat is basically 45. Yeah, because that's the element after before the last one. Yeah, so we sort of starting from the very end, and we're making sure that the max heap property is satisfied at every root node of that particular leaf node and that particular subtree and so on till the very top. Yeah. So in this case, for example, we're now looking at 45. Okay, and we're looking at its parent. In the case of 45, the parent is 14, and the parent has two leaf nodes, two children. Yeah. So one is 2 and 45. Is this so now the subtree that we are looking at is basically this subtree. Yes. And is this satisfying the heap property? So it is not, right? Because 45 is clearly larger than 14, and it is not at the root. So we swap 45 and 14. In this case, clearly 2 cannot come to that position because 2 is smaller. So we take the largest of these three elements and we push that to the root node. Yeah. So in this case, 45 swaps its position with 14. Yeah. So I would be having 45 swapping its position with 14. Right. So this changes. Okay. And then I'm moving to 2. And I have the same scenario here, because we just treated this. Okay. So there's nothing to be done there. Then we move on to 56 and we look at the parent node, look at its child nodes, and we see 55 and 56 are both smaller than 67. So the subtree that we're currently looking at is this one. Yeah, and we are only interested in the child nodes because the way we are progressing, we started bottom up, so which means we would have already treated this. So we have already ensured that 55 and 56, for example, are satisfying the max heap property. Yeah. So we're now looking at 67 and we realize, okay, 67 satisfies, the tree at 67 satisfies the max heap property because it is greater than its child node's value. Yeah. So then we move on to 55 and the same story repeats itself. Yeah. And we are now at 45. And at 45, we look at its parent node, which is 97. And we realize that, okay, 97 is greater than both 67 and 45. Okay. And then we come to 67, the same story. And at finally 97, and there's nothing to go beyond that. Yeah, we are at the extreme root. So now this tree is entirely AP5, we call it. So it is satisfying this max heap property. The way I want to do this, I give you a short introduction to what a max heap is. I mean, you can obviously think about what a min heap would be, where you try to percolate the minimum element towards the top, yeah, and not the maximum. So it's exactly the opposite sort of, right? So, we will stick to max heap for now, because, the min heap would be analogous to what we discussed here. You just have to make sure that you're making the minimum element percolate up rather than the maximum one. Yeah. What I want to now go on to is I want to give you sort of a real problem. Yeah. Because we learn data structures and then sometimes we are a bit clueless as to where should I really be using all this. Yeah. So let's take a very simple scenario. Like, you are developing something like Zomato or these cab services like Ola or something. Yeah. And you have these, so let's stick to the Zomato example. Yeah. So you have these numerous restaurants which have registered with you. Okay. And there is a person at a certain location, yeah, and they are feeling hungry and they want to order something. So they want to look at the nearest restaurants to them. Okay. And they come to your platform Now you have, imagine this, you have like, Zomato is delivering all over the globe, let's say. Yeah? And you want to make sure that you are coming with the 10 restaurants which are closest to this person's location. Yeah. Now I'm going to throw out this problem in the open, and I want to see, what kind of solution you come up with. So let's imagine these restaurants have a location code, okay? And the person searching for the restaurant also has a location code. And there is some function which can find you the distance between two location codes. Yeah? So we don't have to bother about that. How do you find the distance? Yeah. So let's say there is something existing which can basically, given two different location codes on the map, can tell you what is the distance in kilometers between them. Okay. Now your job, as a software developer who is hired with Zomato, okay, is to find out in the shortest possible time the 10 restaurants which are closest to my location. Say I'm that person, I'm the one who wants food. Okay. I want to now open the floor and I want to see, what all different solutions you can come up with. What sort of a data structure would we employ here? And what would our algorithm be? Okay. So I really open the floor, I want this to be really interactive. So I want everyone to pitch in, don't bother if it's a brute force, we just want to talk about algorithms and we want to see why a certain approach would be a good approach and why a certain approach will not be a good approach. Yeah. So I start, I start with one name that I know, and then, Kedar, you should point to someone else. Yeah. So let's start with you, Kedar. What do you think the approach should be?
I think we should use Dijkstra's algorithm to find the shortest distance, and then we'll try to arrange them according to its mini position.
So, sometimes what happens is one of the typical things I've observed. Yeah. We tend to not focus on the problem statement. I call it, the solution becomes the problem. So what happens, it's like someone comes to me and says, Kapil, let's imagine in the 16th century, someone comes to me and says, hey, I have to come to your place for working, and I have to spend 4 hours walking because I stay 50 kilometers away. Yeah. So that person tells me, can you please do something about this? So I say, yeah, sure, why not? And I will create you a Mercedes-Benz car. Yeah, this is 16th century. And then I work for another 50 years and I never deliver that solution, because I aimed too high. Yeah. And I focused on the solution as my problem. The original problem was that the person wanted to travel. Maybe the person would have been happy if I gave them a simple bicycle. Yeah. So let's focus on the problem statement again. The problem statement says, I want to find the 10 closest place, and I already know how to find the distance between the different restaurants that are in my database. So you would have a list of restaurants in your database. You know my location.
So we just have to arrange them.
Yeah, just 1 second. Right, so I have all the restaurants in my database, yeah, and these restaurants are all over the globe. So, let's say I have 100,000 restaurants in my database, yes, and I know their location. I know their location on the map, so I know their X and Y coordinate. Yeah, I know the location of the person who is making the search, so I know my location, for example. So I know these two locations. I know the person's location, and I know the location of every single restaurant that is within my database. Okay, I also have this function which can basically, given two different locations on the map, can tell you the distance. So there's no question of me using Dijkstra's algorithm. Yeah, I'm not trying to find the shortest path. That's not the problem statement. The problem statement is, how do you find me the 10 closest restaurant? You understand? Kedar?
Yes, sir. We just need to arrange the distance.
So we just need to arrange, which means you're saying, what do you mean by arrange? So I have 100,000 restaurants in my database.
Sorting, kind of.
Yeah, sorting. So sorting is one approach. So you were saying, we will sort. Now, name someone who can talk after you, so we want someone else to be involved. Someone you really hate. Okay, so we say, we will sort all the restaurants based on their distance from the customer's location, right? This is what you said?
Yes, sir.
Okay. Now you need to name one person who would like to comment on the solution, whether they agree, they don't agree, they think this is not a good idea, they think this is the best idea. Okay, name someone, Kedar, fast.
Ashish
Ashish.
Shende.
So Ashish, now you know who your real enemy is.
Hello.
So Ashish, what do you think?
Yes, I also think that the data should be sorted. The distance should be sorted, and the first 10 distance should be selected. So,
Perfect. So the top 10 should be selected. Yeah. Does everyone agree with that? Is there anyone who says, no, that's not a good idea? Okay, so if we write something like this, and tell me how much time would take to sort 100,000 elements. What is the fastest algorithm that you can run?
merge sort.
Merge sort. And how much time, what is the time complexity of merge sort? Quick sort, merge sort, what is the time complexity?
N log n.
N log n, right? So if we talk of 100,000, okay, that's a significant number, isn't it? Sorting 100,000 elements is gonna take a good amount of time. So you see that, imagine that you're really hungry, you're on the website and you say, get me the 10 closest restaurant, and then Zomato is taking ages and showing you a nice little circle which goes up and down and up and down. Yeah, are you going to be visiting Zomato after that? Most probably you're not. Yeah, you'll hate Zomato. It takes half an hour to just come up with the 10 best restaurants near you. Yeah. So this approach has a problem. Why it has a problem? It has a problem because you're sorting that, what is 10, 100,000 take away 10? Almost 100,000, right? I mean, it doesn't matter 10, right? So you're sorting those, I don't know, 90,990 elements for no reason, because I just asked you the 10 best. Zomato just shows me the 10 closest. Yeah? It doesn't show me 100,000 which are closest to me, right? So you're sorting those 100,000 when I'm never actually going to use your results. The only thing I'm interested is in the 10 restaurants that are closest to me. So clearly you're doing a whole lot of work, which I'm just going to throw away. You understand? When you're sorting the entire set of restaurants, okay, you are doing a lot of extra work that I will never use, because I was interested only in the top 10. Let's, scale this problem even further down, okay? And you'll understand why this approach will not work. Let's say I'm looking at the closest restaurant to me, not the top 10, but the closest to me.
So we can create a mini and take the root node in this, and the other one we can go for less than 2 raised to n minus 1 less than 10 for the creation of mini.
Okay, I didn't understand partially.
So,
I understood that you said so let's talk about this new problem. Yeah, so the new problem is I don't want the 10 closest, I just want the closest.
Then the root node will work of mini.
Yeah, so in this case, if somebody tells me I will always come and ask for only the closest, I will not even use a heap. See, because which heap are you talking about? The customer's location keeps changing, right? So today I'm searching from here. and tomorrow somebody else would be searching from somewhere else, right? So which mean heap are we talking about? So you need to first create a mean heap, right? Yes, no?
Yes.
Right. And you have to create the min heap out of this 100,000 elements, right?
For
So
every customer.
even that takes some time, isn't it? Right. And if I'm asking for the closest restaurant to me, then I would just basically scan the entire 100,000 elements, and I would look at the one that is closest to me. So that's like finding the minimum element in a list of integers. Yeah, if we were to find, let's say, minimum element in a list of integers, then we would just scan the list and we would take the minimum from there, isn't it? Right. So so now we understand that sorting is not always the best approach, and especially when you don't want to find the relationship between every single element. Yeah. So for example, if I scale the problem further down and I bring it to the closest, then you're obviously suggesting that we shouldn't be sorting, because I sort the entire array and then I only pick the top element. So that means if I wanted to find, let's say, the minimum element, I would just do a simple scan, which is linear order, and I'll pick the minimum element out of the array, right? So I don't need to sort it. Yeah. So clearly I'm saving a hell lot of time there. Yeah. And now coming back to this problem, let's say, I want the top 10 or I want the top 100 elements. Okay. Then obviously I cannot do a simple scanning like I did for the minimum element. Then, so Kedar, what was your suggestion there?
Create a min heap of size less than 10.
Right. So create a min heap of size, how much?
Less than or equal to 10 or 100, whatever the size we want to find. The closest 10.
Right. So we'll create a min heap of size 10. Okay. So what would the algorithm look like? What would we do? So let's say we created a min heap of size 10. And what would be stored in this min heap? Which restaurants would be stored?
Closest 10 restaurants. Distances of 10 restaurants, or maybe name of the restaurants. Name of the restaurant.
So we need to come up with an algorithm, isn't it? We need to be saying exactly what we would be doing, right? So we need to code it up, right? So let's do one thing, yeah. So let's try to write the algorithm here. Okay. Let's create a new file. Let's say erase. Okay, right. So let's try to write the steps of the algorithm here. Okay. So what would this look like? For example, the function signature. So I'm saying, what should I be returning back? I should be returning back a integers, and I would call get nearest. Okay. And what should I get in? I should take in the elements. Okay. And I should be telling how many I want. So the number. Yeah. So for example, what is happening here? I'm saying, I'm going to give you the 100,000 elements here in the elements list. And I'm saying how many I want. For example, I want the 10 closest to me. In this case, let's say we want to find the 10 minimum elements, yeah, in this list. So let's say basically this elements list, the elements thing is nothing but, the distance of those restaurants from me, yeah, from my location. And what we should be returning back is we should be returning back a list of whatever this count is. This count is 10. then I would be returning back a list of 10 elements. Okay. So now let's try to list down the algorithm. You know, what would the algorithm do? So you want to give a shot, Kedar? You know, I'm a bit disappointed. Like I did the last session last time, and there was a really good participation. You know, there was a lot of people who were speaking up. It wasn't just one person. Yeah. So it really feels like, you know, it's a one-to-one session between me and Kedar. I would really urge everyone to speak up. You know, whatever their thoughts are, it doesn't matter. Yeah.
Hello, sir.
Yes.
So should we pass the reference element that from our reference element in the
So what's your name?
Ashish?
Ashish. So Ashish, I'm dumping the problem down, you know, so we are not giving the reference element, because imagine that, you know, this elements list is nothing but the calculated distances, and that too in the form of an integer. The real problem, you know, where we want to find the restaurants we would be fetching data from the restaurant database, and we would be doing a calculation between our location and the restaurant location. And this is the distance that we would feed to this algorithm. Yeah. Because we want to, you know, show something which is much more understandable and readable here. The idea is that I'm dumbing it down. So I'm saying, okay, there's a function which is given a list of integers, okay, random list of integers, and we want to find the top 10 with the minimum value, okay, or top 100 with the minimum value. And the idea would be this minimum value would basically correspond to the distance of those restaurants from the current location. Yeah. So we are sort of dumbing down the problem a bit, but the idea, the concept remains the same. So you can imagine, you know, that if it was a real problem, then it would be something like double. Okay, because the distance would be in you know, floating points, and somebody would have already calculated that distance for me and calculated those elements for me. Yeah. Okay, so what you are suggesting is basically, you know, what you're looking at this problem, which is, you know, create data points. Yeah? So this create data points is basically, say it returns me a list of what I'm going to do in here, for example, I would say open the restaurant database for each restaurant, calculate the distance of the restaurant from the current location. Okay, and this is where you can say I would need the current location. Yeah, so we would say location, which is, let's say, X and Y. Yeah, and then I'd say current location, and let's say location is nothing but a location. Okay, and it has a position, let's say a map position, int X, int Y. Right? And then maybe this is not int, this is float again. And you know, so for each restaurant, so I would open the restaurant database and I would fetch restaurant from the restaurant database. I will calculate the distance of the restaurant from the current location. I'll create that list and then I'll return that list. You know, so right. So obviously, but we are not doing all of this right now. Yeah. What we are focusing on is algorithm part right now. So imagine that, you know, somebody has already calculated this stuff for you. Yeah. And instead of list of double, we make it list of integers, again for just demonstration purpose. It doesn't matter, yeah. But it's easier to deal with integer numbers, especially when I'm demonstrating the working of the algorithm. So that's the reason we are only focusing on this part right now. Make sense, Ashish? Ashish, does it make sense?
Yes, yes.
Yeah. So we are only focusing on the algorithm part. So we are really dumbing it down. We're saying, okay, we have the distance in the form of an integer. We have these 100,000 elements in this list, which is passed to me. And my job is to find the top 10 with the least distance. Yeah. So the distance is already calculated by someone. Yeah. So if the restaurant is in the same building where I am, that distance would come out to be 0. So this elements list would have something called as 0 in there. Yeah.
Yes.
Okay. So now we can focus only on the algorithm part. Yeah. So we were listing down the steps. I would like somebody else to speak up now. So Ashish, name someone else. Fast. We don't have all day.
Pranav.
Pranav. Hello, Pranav. You need to wake up. Is Pranav there? Oh, let me just keep it on mute. It's easier that way. Okay.
Or Kamlesh from the chat box is replying. So
Yeah, I don't see. Where's my chat box? Yes, I can see. Okay. Yes, Kamlesh Vidate. What do you think we should do? You can unmute yourself, Kamlesh.
Sir? Yes, sir.
Yes.
Hello.
Yes.
Sir, what you asked?
Oh, looks like you just woke up.
No, sir.
It looks like that. It was a nice sleep.
No, sir.
Okay. Anyone else who can tell me what's going on here?
sir, can we use graph for this?
Say that again.
Can we use graph?
Yeah, we can use whatever we like. What is the idea? Tell me. So who is telling this? We can use graph.
Ashish.
Ashish. Yes, Ashish. What's your idea about the graph?
So that there were the value of their edges will be the distances. So we can calculate that the least 10 values will be our list.
So you can calculate least values how?
That edges value will be the value of the distance.
Yes, but how will you get me the 10 least values? So yeah, we created a graph, let's say, yeah. So you know what that graph would look like? It is first of all not a graph, okay? Let's try to imagine what it would look like. It's sort of a graph, a very skewed graph at that. Right, so what would that look like? That would look like something like this. My restaurant, sorry, my location. This is me. And then okay, this is me, and this is me here in the center. And I have all these things. Okay. And I would have
It will be the distance from same point only, right?
exactly, right? So how is that helping me? It is just like a list that I've sent in. All that it has is distance of these different points from me. So these edge distances is what we have sent inside as a list in that function, right? So the graph is not really helping me. You know, it's a one node. I mean, obviously there are many nodes, but the only edges that exist in this graph is from the current location, which is my location, to the different restaurants. That's it. Right. This is what the graph looks like. Okay, not very interesting. Yeah, it does not help me save any time or anything. Yeah, so it's basically, when I look at it, it does not look very different from the list that we are sending in, this list. Yeah, and the edges distance is the distance here on each of these edges. Yeah. Remember, we're not doing a shortest path algorithm. I haven't said that, you know, given this location and some other location, what is the best way to reach there? What is the shortest path? And then you say, okay, we should take this and this and this, and then we reach there. We are not doing something like, you know, what Ola does, that they give you two location and then they give you the, you know, they calculate how much fare it would be based on their shortest path calculation. Yeah, how the car would travel from your location to your destination. Yeah, that's not the problem that we are solving, right? What we are trying to solve is basically we want to find the 10 closest restaurants based on their distance from me. So the distance is known. We've dumbed it down. We said the distance is represented as integers. Okay. And we want to find the closest 10, 100, whatever the number is. We want to find those restaurants, right? Okay, so I want to understand, I introduced heap. Can you think of if there is a way to use heap? So, Keda sort of started in that direction, and I would say that that's the right direction to go in. Can we use the heap data structure to solve this problem?
Hello, sir.
Yes. What's that?
Sir, can we partition the array, something like that?
Partition the array. Who is this?
Sir, Vipul.
Vipul, perfect. Vipul, what do you mean by partition the array? So exactly what?
Sir, sir, if we check the last element of array and then just compare the with middle element, and if it is less than elements less than that, then it will left side as like a quick sort.
Like a quick sort, right? So we again doing sort.
Yes. Yes.
Hmm? So I wanted to, maybe I could not get my message across properly. Yeah. So it's difficult to draw things here, especially arrays. But when, okay, maybe Visual Studio is easier actually for arrays. So let's see this. Yeah. Let's take that our input element is composed of these numbers. Okay. Now imagine that this is 100,000. Yeah. Obviously, I'm not writing 100,000 numbers here. Otherwise, we all are sitting here for another month. But try to scale your imagination. Yeah? So imagine that these are not just 7 numbers, but these are 100,000 numbers. Yeah. I want, let's say, the top 3 numbers. Okay. And in this case, for example, the top 3, I mean, given this list, for example, only this list, the top 3 numbers would be 8, 0, and 12, 12, right? And in fact, let's say, I'm asking for only top 2. So you get the gravity of what I'm saying. Yeah. Now, in order to get top 2 elements, I'm going to sort the entire array. Now, what does that look like? And when I sort the entire array, it looks something like this. Right? So imagine that, I only needed the top two, but you also made sure the rest of the elements are also in their proper order. Now imagine, you have these restaurants, and like I said, you are a sprawling business and you are all over the globe. Yeah. So in your database, you don't only have restaurants in Pune area, but you have restaurants in Mumbai and India and outside India and everywhere. Now imagine there's a restaurant somewhere in New York. Okay. I'm sitting here in Pune, but you make sure that you're putting that restaurant in New York in its proper position. Does that make sense? So you're making sure that the restaurant in New York is in the position 90,999. How does that matter to me? I'm looking at the top 10. I don't care what the other restaurants, which one in Kabul, the one is closer to the one in New York. I don't care about that part. I only care about the top 10 that are closest to me. So we are doing all of this work that you've done from 12 to 99 is basically extra work. You've done something that I didn't need. Yeah. And obviously that takes time. That takes a hell lot of time to sort every single restaurant on the planet. Why would I do that?
सर हम लोग एरिया का कंस्ट्रेंट डाल सकते हैं क्या, मतलब कि फॉर एग्जांपल एज यू सेड कि मतलब हम लोग ऑल ओवर ग्लोब के क्यों मतलब डेटा लेंगे. मैं पुणे रीजन में रहता हूँ तो मतलब 10 स्क्वायर किलोमीटर एरिया की मतलब लूंगा मैं, ऐसा कुछ.
Yes, डाल सकते हैं, but this will work in a certain context. So obviously, when we look at, let's say, how Zomato is doing it, okay, clearly Zomato is not getting the 100,000 restaurants and then trying to figure out the top 10. Yeah. But when you say about the area also, right? For example, I say that, the restaurant should be within a certain area. Now, in this case, you can say that, I will always find a restaurant, let's say, within that area. But let's say we are dealing with a problem where I don't know what the closest one is at. So for example, it can be that, I'm looking at some commodity which is not as easily available as food. Then I don't know where to stop. I don't know where to draw that boundary, right? So in that case, the suggestion that you're making, so that's a pragmatic suggestion. Yeah. So we would obviously, depending on the problem at hand, we would be employing a whole lot of such pragmatism before we arrive at a point where we want to use an algorithm. Yeah. The point is that I'm trying to map a certain problem to the application of a certain data structure. So in the very specific case, for example, there would be other approaches that one will take before they come to the point where they want to apply the algorithm. So yes, what you suggest is a pragmatic approach, and this is definitely something we should be doing before we come to the point where we want to then get the top 10. Yeah. But for example, this approach will not be possible in case where you don't know what is the closest one to you. Okay, so that, for example, if I say that it should be within the area of 1 kilometer, yeah, then it's quite possible that I don't get 10 restaurants. Yeah, and I wanted 10 restaurants. So had I gone to 2 kilometers, I would have got 15 restaurants, right? So right now, let's say we don't deal with the, so we are not dealing with the actual problem, like, for example, we're not doing what exactly Zomato would do, yeah, but we try to look at this problem in a more holistic way, and we say, what is that, for example, we can do to really speed this up, yeah, and what data structure really best suits for this job.
Sir?
Yes?
Can we use tree data structure?
Yes, we can use tree data structure. So, very interesting, everybody says, can we do this and can we do that? And my answer is always, yes, we can do that. We can do everything that you like. Yeah. The question is always, you have to have a backing reasoning to it.
हाँ सर, अगर हमने ट्री डेटा स्ट्रक्चर यूज किया है, उसमें से 8 ट्री डेटा स्ट्रक्चर यूज किया, तो वो की एज अ मिनिमम डिस्टेंस लेगा और फिर वो अपने सब ट्री में सर्च करेगा।
Say that again. You talked about R tree.
हाँ,
Yeah, say that again.
मीन्स वो की क्या लेगा की ऐसे मिनिमम डिस्टेंस की लेगा और वो अपने सब ट्री में सर्च करेगा कि कौन सी फाइंड आउट करता है। अगर वो सेटिस्फाई होगा तो वो 10 एटम्स वो मीन्स 1 by 1 वो कंपैरिजन करेगा अपनी सब ट्री में, और अगर उसको मिला तो वो रिटर्न करेगा।
Right. So typically, for example, for such distance, if you want to find closest one, you would be using an R tree. Yeah. But an R tree needs to be created from a static data source. Yeah, initially. And there's a lot of preparation time that you have to spend in order to first create the R tree. And once the R tree is created, after that, you can start querying the R tree. Yeah.
Yes.
Now, this is a very beneficial thing if the number of queries that you fire to the R tree is over a longer period of time. So it's like, for example, we do some groundwork so that we know the query time would be reduced eventually. Yeah. So we are sort of willing to put in a bit of extra effort at the beginning, because we think there would be a lot of queries that would be fired, and the query time would be less. Yeah. So we are looking at an amortized time there. So we are saying, okay, we are willing to put in a lot of time at the beginning to prepare this data structure, and eventually, because there will be so many queries that would be fired at us, that the eventual query time, we can look at all that and we can say, okay, the query time went really down. So taking into that consideration everything, even the groundwork that we did. So first of all, you have to sort of create an R tree, which takes its own sweet time. And in this case, the problem that we are trying to solve, you're going to fire this once and then you're going to forget it, because somebody else sitting at some other location is then going to fire again. So the data structure that I created, for example, is useless after that point one. You understand?
Yes, sir.
Right? क्योंकि आपने जो R tree बनाया वो मेरे point of view से बनाया।
हाँ,
मैंने वो 10 रेस्टोरेंट मिल गए मुझे, मैंने एक को चूज किया, खाना मंगा लिया, अभी कोई और फायर करेगा क्वेरी को, राइट? एंड उसका लोकेशन और मेरा लोकेशन सेम नहीं है, सो आपको ये प्रॉब्लम फिर से रिपीट करना है, सो आपको फिर से R tree बनाना है, राइट? So that would have been useful if I am the only guy who's firing all the time. Okay.
Yes, sir.
So in this case, it's probably not the most beneficial. I mean, yes, R tree is a really good data structure, but if you are firing good amount of queries at it.
Yes, sir.
So the hint is that yes, we are going to use the heap data structure. Yeah. Now the question is, how should we be using the heap data structure to solve this problem? So Kedar, you started. Would you like to continue?
Sir, we'll divide the given list of elements into smaller list of elements, like divide and conquer approach, and then we'll compare the parent node with the left node and the right node. And if it is lesser, if it is great, if the left node is lesser, we'll replace it with the parent node, and then we'll again continue for the same node.
Right. So one of the things I would like to sort of tell everyone here, whenever there's a problem given and you're supposed to be designing an algorithm, the algorithm should be stated in a way that even your parents can understand. Right? We typically, what we do is we get into some very technical detail and we start talking about, something, I should modify that pointer and make it this, and then I don't understand. Yeah. When you talk about the top level algorithm, it should be in a language that your kid can understand, that your parents can understand. Right? So let's start at the very abstract level, Kedar. Yeah. So I don't understand everything that you said about I will do compare this left and right, and I did not understand anything. Yeah. Talk to me in a language, right? For example, try to think that you're explaining this to your parents, and I'm my parents, for example, who are not computer savvy. Yeah. Okay, so let's give it a shot again.
Hello, sir.
Yes.
Can I try?
Yeah, sure.
Okay, sir. As you said, we will use heap. So what we can do is we can arrange the heap max. We can use max heap, and the one that is our point, can be compared with the max heap value. And if the point is nearest to our, if the point is nearest to our max heap,
which point are we talking about?
the point at the max heap and the point which we are considering, like our current location.
No. So who's speaking?
Tushar.
Tushar. So Tushar, there is no current location now. Yeah, because the distance has already been calculated from the current location.
Okay.
So ये जो elements का list जो आपको दिख रहा है line number 18 पे,
yes,
that already has been calculated based on your current location and the restaurant's location. So ये calculation already हो चुका है. अभी हमारे पास सिर्फ distances है और simplify करने के लिए हमने वो distances double में न रख के integer में रखे हैं.
Then sir, we can just use max heap. The maximum value will be at the top and we can pop out the maximum, I guess.
Yeah, so see, I want to have a sequence of steps. Yeah, what is an algorithm? You know, so I was just sort of overhearing my son's class, and the first thing they teach them is, you know, what is an algorithm? And the first thing they teach them is they say an algorithm is a sequence of steps. So there's a step 1, there's a step 2, there's a step 3, and there are things like, okay, now go back to step 1, okay, or go back to step 4, something like this. Yeah. So that is the level at which I'm expecting you to help me out with. Yeah. What is the first thing I should do? So everybody's saying, okay, we have the max heap and there is element at the top, but tell me, you know, I have this list of elements here. Okay. What is that I should start doing? So let's say there is a heap data structure. Yeah, there is a max heap or min heap data structure with us. Now, how should I be really using it? So how many of you have used heap data structure before? How many of you know how it works? Have you ever written a heap data structure yourself?
Yes, sir. I have.
Was this a part of your course work?
Not really, but it was mentioned in the course.
Okay. Okay. So that's Kedar, is it?
Yes, sir.
Yes. So Kedar, let's try to give another attempt. You know, so don't try to be too technical about left and right, but give me a very high-level overview of the steps.
So we'll first divide the given list of elements into sub like we'll treat it as a sub problems.
No, so that's okay, fine. So exactly what should I be doing? Like
Dividing this given list, that is the number of distances, into sub distances where.
No. So what do you mean by dividing?
Dividing means, sir.
I should create what?
Grouping.
Yes, but what? Grouping, dividing, what? So what should I write? So what do you mean by dividing? Like, should I create two lists now, two different lists?
No, sir. We'll just divide means we'll just separate it from the same list only. We'll just work on those 3 elements or 3 elements, 2 elements, or 1 element of the same list.
Okay. So exactly what should I do? So I don't understand what you mean by dividing.
Sir, can we arrange these elements in ascending order also?
And what does that mean?
Means we get at one side the smallest element and the highest element in the other side. And so we want only nearest distance. So we find only the smallest element. Means
May I know your name, please?
Manjiri.
Manjiri. So who can answer Manjiri? So basically, Manjiri, you're saying when you say arrange them in ascending order, basically you're saying sort them.
Actually, yes, sir. I was thinking that also. But
And can you tell me why is sorting not a good idea here?
because, sir, we are also sorting the unwanted elements also here, because
Exactly.
we don't.
Right? Because I'm looking at only the top 10 and you're going to
Yes.
sort every single thing.
Yes, sir.
Yeah, and that's a lot of work.
Yes, sir.
Unnecessary work, basically.
Actually, this ascending or arranging in ascending order is also one kind of sorting, actually.
It is sorting.
Sorting.
When you say
Yes,
arrange
sir.
in ascending order, you're just trying to trick with words.
Yes,
Huh?
sir. Right.
Computer does not understand that. It will think you're still sorting.
Hello, sir. Sir, what if we consider the first element as the max element? Then the later second element will be compared with the first element and placed if it is smaller to the left and if it is larger to the right, and then go on placing the next element comparing with the last element. This will let the highest maximum at the top and later to the bottom. We'll compare the first element with the second and the.
Are you sorting? Is that sorting?
No, sir. If we get the we'll consider the first element as the maximum, then we'll place it as the root, and then the second element will be compared with the first element which we placed at the root node, and if it is smaller, it will be placed at the left side of the root, and if at the larger, then we'll get the maximum at the top.
Okay, if it's larger, then what do we do?
We place it at the right.
Okay, and then what after that?
Okay, sir, I'm a little stuck. I'll just think about it a little, because the larger one must come at the root again. Then I think the larger one will again be called, will again be considered as the root.
So which data structure sort of has this property?
I think we would have to rotate it a little.
We are again getting
like
into
AVL.
details of them. No, we are again getting into details of implementation. What is the abstract idea that you have?
I'll just think and answer.
So the idea is, what we are all getting at is that we want the larger element at the top.
Yes, sir.
So imagine this. You imagine you're doing this, yeah. So let's say there is some magical data structure. It is not magical, it's HIP, yeah, which is maintaining the 20 restaurants which is closest to you, or the 10 restaurants which is closest to you up to this point. Okay. Yes. So let's say I see the first restaurant in the database. Now I don't know, maybe that is at 100 kilometers, but I get this restaurant. This is the first restaurant that the database returns me. Yeah. And I look at my current set of restaurants which are closest to me. Okay. And right now I haven't got any because I'm just starting, right? So this is my first restaurant. I look if I have anything in my list of 10 restaurants and I see kuch bhi nahi hai. So I say, okay, kuch bhi nahi hai, iska matlab ye closest hai mere liye. Right na?
Yes, sir.
So I put that restaurant in my list. Okay. Then I come to the second restaurant. The second restaurant happens to be at 50 kilometers. So then I say, okay, clearly वो 100 था, ये 50 है, लेकिन अभी 10 restaurants हो गया क्या नहीं हुआ. So ये 50 वाला भी उसमें जाएगा list में, right? And here I try to maintain in such a way that the restaurant that is the furthest from me is at the top. Okay. So which means the restaurant that is at 100 kilometers is now coming at the top. Yeah. So imagine like a heap data structure. Yeah. Then I look at the third restaurant. The third restaurant is at 1000 kilometers. Okay. Then I bring it and I look at my list and I say, am I done with 10 restaurants? It says, no, you're not done. There's only the third one. Then I say, okay, then this restaurant needs to go into my list. Okay. And I'll again look at and I say, okay, 1000 is clearly more than 100. So I'm going to create a heap and making sure, you know, because it's heap, I always make sure that the one that is furthest from me in this list is at the top. Okay. So let's try to grow this a bit. Okay. So let's say I'm maintaining a heap of 10 elements, yeah, because that's what I'm interested in. So the first element that comes to me is 100. Okay. Now, because my list was empty, I did not have a single restaurant that was closest to me yet that I have found. So I put that 100 into my list. Yeah. Then I come to the next restaurant. So let's put the restaurants in that order here. Yeah. So let's say the first restaurant is at 100 kilometers, then the other one is at 50, then there is one at 1000, then there is one at 34 kilometers, and there's one at 777 kilometers, and 89 kilometers, and 2 kilometers, and 90 kilometers. And let's say we're not finding top 10, we are finding only, let's say, top 5, yeah, to make it, keep it simple. So now I look at the next restaurant that comes in, yeah. The next restaurant is at 50 kilometers, okay. So what should I be doing? I need only 5 restaurants, yeah, let's keep that in mind. I'm looking at only top 5. Okay. The next restaurant that comes in is at 50. Okay. What should I do? Should I put that restaurant in my list? I want 5. Should I put that in my list? Yes, no?
Yes.
Yes, right? Because I'm not done with 5 now. Or मेरे को आगे का नहीं पता. Maybe there are only 2 restaurants in the database, right? So I don't know whether, you know, that this 50 wala should be out when, you know, from my perspective, I need 5 and I have seen only 2. And clearly these 2 are within the top 5 right now at this point in time, because I haven't seen the rest yet. Yeah, so imagine that, you know, this thing I haven't yet seen. Yeah, so I only looked at 150 and clearly they are within the top 5 for now. Yeah, so I create another one, and this is, let's say, a max heap that I'm keeping. Yeah, so in max heap, what would happen? Oh, okay. So max heap mein okay, so I create this restaurant, okay, and this is a heap data structure, a max heap data structure, and satisfying its property. The one that's furthest, now which is furthest in this? 150, clearly 100 is the furthest from me, and therefore I keep it at the top. Yeah, so I'm sort of using the max heap property. Then the 1000 one comes in. Should I accept the 1000 here? Wow, that's interesting. I didn't understand the language though. So now 1000 comes in. Okay. Should I accept 1000, Wala?
Yes.
Yes. Why yes? Why yes?
Because we don't know the other elements.
Right, because I'm looking for top 5 and I've seen
yes.
3, and this fits in the top 5 right now, right?
Yes. The
okay.
4th might be greater, even greater.
Exactly, right? So I very nicely put in 1000 also. Okay, and I do this, and then what happens? Is this max heap?
No.
No, it's not. It's not max heap, right? So what should I be doing to make it a max heap?
So 1000 at the top.
Exactly. So I should be swapping these 2 locations, isn't it? So this should go here, and this should go there, right? So we make that happen. Okay. So we swap the 100 and 1000's position. and you will understand, why that's interesting. Okay, so I'm making sure that the furthest is always at the root, and for each of the subtree also I make sure that. Yeah, so now we'll come to that. So let's say now I look at the next one, which is 34. Let's put in some more numbers to make it a bit more interesting. 44, 120, 7, 8, 2, 3. Okay. Now we are at the 34. Okay, should 34 be put into my list of restaurants? Yes, right, because I've still not hit the 5 figure. Yeah, so I put 34 also. Okay, and 34 goes here. Okay, the next is a 0th index, first index, second index, third index. Okay, so okay, so third index. Okay, and I put 34 here. Okay, now after putting 34, am I satisfying the max heap property? I'm satisfying it here. I am satisfying it here because it has no children. I am satisfying it here. Am I satisfying it here?
Yes.
Yes.
I am, right?
Yes.
Because clearly within this subtree, the furthest one is at the root. So I am satisfying the max heap property. Perfect, guys. Yeah. Now it's warming up. Okay. So then I go to 777. Should I be keying 777 in?
Yes.
Yes, because I still haven't hit the magical figure of 5. Okay. Because I'm looking for top 5, isn't it? So, okay. And this is what? So this is what? 777. Okay. Now what should happen to 777? It comes in here. Now, then I once again inspect my max heap and I make sure that the max heap property is satisfied everywhere. Is it satisfied everywhere?
No.
No, sir.
You know what? We did one mistake, by the way. When we started, the 50 should have been on this side, because that's 0, 1, 2. Yeah. So we will make it like that. And this is actually 100. Yeah, because see, the 50th had come down and the so 100 and then 1000 came in here. Was I right?
Yes, sir. Yeah, this one is correct. Because
right, right?
yeah, 50 should be at the first index.
Yeah, because this is 0th 1. So 100 came at 0th, then 50 at 1, then 1000 came in at this position. So 1000 was swapped with 100. So 100 should have come down here. Yeah, okay. On that case, I think I started with the right node first, and then I came to that. Yeah. Okay, now back to this question. Is 777 at its proper place?
No.
It is not, right? Because I look at this subtree and I say clearly 777 is bigger than 50. So by the max heap property, 777 should travel up. Yeah. So I make this go here. Okay. So let's do that. So 777 comes here. What is there? 50. 50 comes down. Now is the max heap property satisfied? Yes? No? I don't care.
Yes.
Yeah. So it is clearly satisfied, right? At every node. So the leaf nodes, there's no question because they don't have children. At this node, for example, 777 is clearly bigger than these two, and 1000 is clearly bigger than 777 and 100. So it is nicely satisfied. I've got my 5 restaurants filled up. Yeah. Now I go to the next one, and 89 comes in. Abhi kya karna chahiye? Now we are at a crucial junction. What should we do? Now 89 is there. Come on.
We'll compare it.
We don't have to, this is very common sense stuff. Yeah. So it's not, you don't have to be a computer science genius to really answer this question.
We'll compare it with the last element of the array.
Last, that means 50.
Yes. And if it is greater, we'll replace. If we are creating max heap, I think so.
So 89 is greater than 50. So what should I do?
So we'll replace it.
We'll replace 50 with 89?
Yes, because we want top 5, right?
And so top 5 may, you don't want the top 5 as the furthest from you. You want the closest to you.
So we'll keep it as it is then.
Sorry?
So we are creating max. Okay, we'll keep it as it is then.
I don't understand.
We will replace it by first we will replace it by root, and then we will again swap.
Right. So the thing to understand here is we kept, we have one restaurant which is at the root, and we know that is the furthest to us. Yeah. Abhi tak jitna dekha hai usme ye furthest hai, और उसका distance है 1000 kilometers. जो नया restaurant अभी मैंने देखा, that is at 89. Right, and my list is full. Yeah, so 5. I had only 5 places. The 5 places are occupied. Okay, which one should I throw out? The furthest one, na?
1000.
Yes.
I will throw the 1000 one out. I will say goodbye. Yeah, I don't need you anymore because I found a better one. Yes, you're right, Monica. Yeah, so I'm going to basically say I want to replace the root node value with 89. So first of all, what am I checking? I'm checking whether 5 has been done or not. If 5 is not done, then I was simply inserting things. Yeah, but now 5 is done. At the point 5 is done, I'm saying, okay, I cannot insert anymore because 5 is done because I only wanted 5. So I'm going to say, okay, look at that node and say, which is the one that I can throw off. And clearly the way we maintained that list, yeah, we maintained the max heap properties. This was the whole reason why we created a max heap. So the furthest can be at the top. So it's very easier for you to look at the root node and say, hey, you are at 1000, clearly you need to go out. Yeah. So that's what exactly I'm going to do. I'm basically going to throw 1000 out and I'm going to replace that with 89. And then I'm going to ensure whether my max heap property is satisfied or not. Right, so whether you insert an element or whether you replace an element, the first thing that you always do is you make sure that your max heap property is satisfied. So let's see whether it is satisfied or not. So 89, 777 and 100. Is it satisfied?
No.
No, sir.
No.
What should we do?
70 is with 89.
Precisely. Yeah. You see why this max heap is really helping us out? Because it always ensures that the maximum element is at the top. So it becomes very easy for us to throw it off. Right? And we bring this one down to this position. Yeah. So I know I'm not very good at drawing, I should be doing arrows and all that, but not an easy. So that's exactly what we're going to do. We're going to replace 89 with 77. We're going to swap the position. 777 comes here, and 89 goes there. Okay, and then I question this again. Is this satisfying the max heap property? The tree at this node. Take those arrows off now.
Yes.
Yes.
Yes, so I look at this particular one and I say, is the max heap property satisfied? I look at the root node and say, oh yeah, clearly greater than 3450, so satisfied. Great, nothing to be done. Yeah. Then we go to the next one and we say 2. Okay, so now 2 comes in here. You see, it's very important to understand why the max heap really helps. Because you are removing one at a time and you're making sure that you're removing the furthest one. Yes. So now again we go by the same logic and we say, okay, clearly 2 is less than the root 1, so the root must be thrown out. Okay, and that's exactly what we do. So we replace. So I'll now go a bit quicker. If you don't understand something, please let me know. So 777 is thrown out, 2 is here. Clearly, this is not satisfied. So 100 needs to pop up, 2 needs to come down. So just point out if you're not understanding something. Yeah, I think, but by now everyone is getting comfortable with this. Yeah, 90. Yeah, now 90 is again less than 100, so 100 needs to go out. So I bring 90 here, and max if property is already satisfied. Yeah? So 90 is the largest number so far. 44 comes in, 90 goes out now, and 44 clearly the max if property is not satisfied. So I'm going to swap 44 with 89. So now 89 goes up. Yeah, and then in here again I make sure that it's satisfied. So 50 should come up, and 44 should go down. Okay. And then 120 comes in. 120 is already greater than my greatest furthest one so far. So what should I do? Hello?
You should not insert.
Yeah, I shouldn't do anything. You know, I should just look at 120, look at 89, and then throw off the largest one of them. Now the root is already smaller than 120, so I don't need to touch my list. I need to just throw 120 off. So I throw 120 off. Then I come to 7. Now 7 is clearly small, so I need to throw 89 out now. And then 50 needs to travel up. Okay, so 50 and 7 comes down in 50's position. And then 44 needs to travel up. So 7 comes down to 44's position. Okay, and then 8 comes in, and 8 is clearly smaller than 50, so 8 comes here, but 44 is bigger, so 8 comes down, 44 takes its value. Okay, but then I look at this particular root node and I say, okay, 34 is bigger, so 8 should come down, and 34 should travel up. And then I look at 3 and I realize, okay, 3 is smaller than 44, so 3 should come down. But then 3 and 34 are not satisfying max. So 3 should actually be here and 34 should actually go up. And that's it, done. Are these the closest among these? Yes, no?
Yes.
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 You also notice that what was the storage that we used? What was our storage like? How much extra storage did we use?
5 spaces.
5 spaces. Now this is the most important part. Why the heap really makes sense here. So imagine this, you know, you have 100,000 restaurants and you want to find out the top 10. Now the 10 in front of 100,000 is minuscule. If I was to do any sorting business, I would need all of that in memory, no? Or I have to have some really complicated sorting algorithms which work from the disk also. But imagine that, you know, everything that you've done so far, quick sort, merge sort, all of that elements need to be in memory, right? Which means the sorting, for the sorting to take place, I need 100,000 element spaces. Okay, and that's a significant amount of memory that I need. Okay, whereas with this particular approach, you know, I always kept track of only 5 elements. I never kept track of 100,000 elements. Now, the wisest among you would say, hey, but what about this array which had 100,000 elements? Wo to waise bhi tha. I could have sorted that, right? So that's a very valid point, you know, but when we are actually doing things like this, we never dump the entire database in our RAM. We never go to the database and say, hey, give me all the restaurants over the globe. And then, you know, the database is churning data and churning data and churning data. Yeah. And by the time the customer is already gone. So we don't do it this way, basically. Yeah. So typically the way this is done, you know, we get 100. So because we don't have that sort of an infinite memory with us, we get the first 100 and then we are processing on that. While the first 100 are being processed, we are fetching the next 100. Yeah. So at a time, for example, I would only be ever fetching 100 values. Now in sorting to work, I would need all of that in memory at once. So actually my database would have to fetch all the elements, give them to me. I would have to allocate that kind of a memory, then do the sorting business, and then eventually throw everything off and take the top 10. Yeah. So now you understand why that approach of sorting, right, would be crazy slow, would need a hell lot of memory, and would eventually be something that, you know, our customers will not like. On the other hand, doing it this way, I can do this more, you know, we call it streaming data. You know what streaming? Basically, because I never need to see the entire data at once because I'm not sorting them. I'm only looking at 100 values at a time. I'm feeding it to my list, and, you know, I'm throwing off the rest 90. I'm keeping the top 10 with me, right? Then I'm looking at the next 100, comparing with my top 10, you know, basically what the sort of comparison that we did right now. And I keep throwing and keep throwing and keep throwing. Yeah. So I never need the 100,000 at once. Does everyone appreciate that? Hello? Has everyone gone to sleep?
Yes, sir.
How many of you still have the energy to actually implement it like a working code? Should we do this?
Yes, sir.
Maybe I just hear one.
Yes.
If I get
Yes, sir.
Yes,
confirmation,
sir.
then we should do it.
Yes, sir.
Yes, sir.
That's nice. Yeah. So let's do this. Okay. So one of the first things we would do is we would create a heap data structure. I'm going to warn you, right? This is going to take some time. Yeah, but I wanted to do some practical hands-on with you. And it only made sense to actually show the implementation. Yeah. So what is this heap thing is actually going to do? You know, we talked of this concept, you know, like we talked of this thing that, you know, I want to insert an element into my list. Yeah. So you remember when we started with one node. Yeah, we started with one node, and the one node was 100. Yes, remember?
Yes, sir.
Yeah. And then we said, okay, I need to put in another one, and 50 came in, and then 150. So yeah, okay, that was the same. And then 1000 came in, and we swapped its position, right? So we need to sort of implement that. Yeah. So what we're going to do is we're going to create a heap structure. So what this thing here is my max heap data structure. This is my map heap data structure, max heap data structure. Yeah. Okay. Fine. Anyways. Okay. Yeah. So this is my max heap data structure. Okay, and this is what we are going to implement basically. Yeah. And then we are going to implement the algorithm. So first we need the data structure. So there are two parts to it. Yeah. So I would like everyone appreciates that two parts to this whole thing that we've done. One is the algorithm that we wrote, which I described in steps, you know. For example, let's try to write that algorithm first, you know, the one we described. Okay. So what did we describe now? You know, now coming to the point that I was telling you all that, you know, how you describe an algorithm in the first place. Yeah? So rather than getting into the details, you should say, I would say maintain a max heap data structure to keep track of the 10 closest data points. In our case, for example, restaurants, yeah, but can be anything. Okay. So I need to, okay, whoever reads this understands, okay, I have to create a max data structure. Fine. That's point one. पढ़ने से क्या चलना चाहिए? हाँ, कि हमको क्या करना है? Then what is the next step? Process, read the next element in the input list. I'm not saying, things like start with I equals 0, then read the element at I, and then somewhere increment I and all that. And try to keep it simple. So I'm saying read the next element in the input list. So if you're starting, you're obviously reading the 0th element. Yeah. Then what should we do? Check if we already have filled up the max heap. Okay. If not, then what should I do? Insert the element into our max heap data structure, making sure that the max heap property is always satisfied. Okay, that I'm just writing it for your reference, but when I say max heap, I by default expect that. Yeah, therefore I call it the max heap data structure. I expect that its max heap property would always be satisfied. Okay. If yes, what is this if yes wala root path? That means we have already filled up the max heap with the requisite number of restaurants, with the requisite number of data points. Yeah. So if I have already filled that up, then what should I be doing? Can somebody help me out here?
Go to second point, sir. Read the next element.
Say that again.
Go to second point. Read the next element in the input list.
No, but यहाँ पे क्या करूँ? I've got yes. That means I've already filled up the max heap. अभी क्या करने का? ये data point जो मेरे हाथ में है. So I've already read the next. Na?
Compare it with the last.
Compare it.
Perfect. So I compare it with what?
Farthest element.
And where is the furthest element?
Root.
Root node.
So
Check
I
for
would
the
say
root.
compare it with the root element. Okay. Then we say if the root element is bigger than the compare it with the root element. Yeah. So let's say the case is root element is bigger. So what should I be doing? If the root element is bigger, what should I do?
Replace.
Sorry?
Replace it with the
Replace, exactly. So I need to replace the root element of the max heap with the current element. What I would like you all to understand here, because this is a 2-hour session, yeah, so I'm not teaching a data structure class here, yeah. What I would like you to understand, some key takeaways from this should be how you go about thinking about an algorithm. What are the challenges and things that you have to think when you are employing an algorithm or a data structure to solve a given problem at hand. For example, one of the things that I've always noticed where people really struggle is describing an algorithm at a top level step, at a very abstract level. What that always tells me about the person is their clarity. Because if you can describe the algorithm in plain English, now, maybe our parents don't understand max heap, yeah, and my child would not understand max heap. But for example, I can tell them that, some structure, which always keeps the top element at the top. The largest element at the top. Yeah. But apart from that little detail about what this max heap thing does, if you look at these steps, they are in absolute plain English. They tell, compare this, do that. It's very simple plain English. Yeah? If you can't describe an algorithm in this way, I will assure you that most of the times your approach is not right. Because you are not being able to get down. We say, when we are ambiguous about a situation, we go into some corner detail. That's what we start talking about. We say, compare I with I plus 1 and do this and do left, right, and all that, right? We if you understand what you're going to do, right, you will be very easily able to explain to me something in a very high level language. Yeah, and that always tells me the clarity of your mind. Yeah, so whenever I am interviewing and people can describe me things at a very abstract level, okay, then I realize whether they truly understand what they're going to implement or not. So keep that in mind. Yeah. Okay, so we were here. Root element is bigger. Now the other would be root element is smaller. So what should I do then?
Compare that element with the sub elements, and if we get the higher
Which
element,
sub-element? No, see, again, we are skipping which sub-element should I compare it with? All sub-elements?
yes, all.
Left side
Okay.
of someone.
Child.
So why would I compare this with all sub-elements? Who said that?
So Monica.
Monica. Okay, Monica. So why should I compare it with all the sub-elements?
So we are checking if
So we go back to this. We go back to this point. Huh? Wish I could sort of go back in time, but nevertheless, okay. So let's bring it to a certain level here. Oh no, there's a lot of work, huh? Okay, एक काम करते हैं. एक पीछे जाते हैं. 34 हो गया. Okay. यहाँ पे और एक एलिमेंट ऐड करते हैं 55 और उसके बाद और एक एलिमेंट ऐड करते हैं 0. ओके, सो हम यहाँ पे हैं. अभी हमने 3 देख लिया है. अभी हम 55 पे आते हैं. सो वी आर एट दिस पॉइंट. सो रूट एलिमेंट क्या है? 34 है. नेक्स्ट एलिमेंट जो इन माय हैंड एलिमेंट है वो क्या है? 55 है.
yes sir.
Compare it with the root element. Yes. If we already have filled up the max heap. Have you filled up the max heap?
Yes sir.
Yes. So I am here in this path. Compare it with the root element. What is the root element? 34. What is my current element? 55. Compare. Which path will I be at? Root element is bigger, root element is smaller.
So 55 is greater, so we will not take that element.
So where am I? Root element is smaller.
Yes.
Okay. Root element is smaller, then you're saying I should now take 55 and compare with other elements.
No sir, 55 लेंगे ही नहीं ना अगर
हाँ, तो आपको क्या बोलना है? आप बोल रहे हो compare with sub elements. क्यों करना है compare?
We will skip that element.
We should not
skip that element. Yes.
replace.
Yeah, we should throw it in garbage. Yeah, because it's useless. I have better things at my hand in my list. Right? It's like, you know, I have a restaurants which are within 1 kilometer and then another restaurant comes from New York and I'm saying, oh, I should now compare with all the restaurants that I have in my list. Yeah, it doesn't make sense, right? Because if it is further than my root itself, then it is obviously further than everything inside my, nah, because this is the largest. इसी से further है, तो इनसे तो further होना ही होना है. Okay, so I throw it basically. We shouldn't see garbage. Yeah? Throw it away. Okay, so basically don't consider it. Huh? And then what should we do? So now that's done. So we should say go to step. Right, that element we have processed now.
Yes sir.
Yeah, so what should I do now? Now I should be looking at the. So once we have done, we have taken 55, it is bigger than 34. So we realize we should throw 55 away, basically not do anything. Yeah. Then what should I do now? I have thrown 55 off. What should I do now? I should go to the next element. Right. So I should go to step. This is all, the entire algorithm is these 4 steps. Does it make sense to everyone? Like, is this session
yes sir,
enjoyable? I mean,
Yes, sir.
yes sir,
Yes, sir.
Yes, sir.
Yes, sir.
Okay, perfect. So I hear a few voices. I hope they are representative of the entire class. Okay, so we have to now write this implementation, isn't it? But I believe, now having done it in English like this, I think it shouldn't be too difficult for us to really write our code. Huh? So who is going to help me? So it says maintain a MaxHeap data structure. So I should create a MaxHeap. So let's call it a MaxHeap class. Just try to think you have a MaxHeap class. Yeah, right. Let's rename this. Let us call it MaxHeap. Yes. Okay, so I have a nice MaxHeap class with me now. Okay. So I created MaxHeap as R4. Okay. How many elements would my MaxHeap have? How many elements do I want to keep track? Let's say count. Yeah. So I don't know. This is user will send me. User bolega 10 chahiye, 10 hoga. User bolega 5 chahiye, 5 hoga. Now this is shouting at me because it thinks constructor nahi hai jisme integer. So we need to create a constructor for MaxHeap, right? Okay, and it should take in a count. Okay, basically this is nothing but capacity. I'm saying, how many elements should in this case, if you remember, I had a capacity of 5. Yeah, is everyone still following me?
Yes, sir.
Hello?
Yes,
Yes.
sir.
Yeah, please keep saying yes. Yeah, because all I see is a dark Visual Studio window. I don't see any of your faces, so I don't know whom am I talking to. Okay, so we need to keep track of this capacity, isn't it? So we say int it's a property, right? So we say prop, it's int, and this is our capacity. Okay, we are never going to set the capacity. We are always really going to go get it. Capacity, sorry, capacity equals capacity. You all know this constructor business and objects and stuff. I believe you guys know this, right?
Yes, sir.
Yeah, so you're understanding what I'm doing, right? It does not feel like magic, right?
Yes.
Yes, sir.
Yes,
What
sir.
languages have you done so far? You've done C, C++, or something like that?
Yes, sir.
Yes, sir.
You done C++?
Yes, sir.
Yes, sir.
Yes, sir.
This is bigger brother of C++ or younger brother, whatever. Yeah, so this is C#. Yeah, and as far as the syntax goes, okay, right, that I could understand. So this is C#. I'm writing my code in. For most practical purposes, to me, there's no difference between this and C++. So you have the concept of a constructor in C++ also, and exactly I have it here. You have your public or private member variables. This is a property which is like a member variable, and I'm initializing its capacity. Yeah, and this is basically to represent this fact, because we said, for example, I only want to take top 5 or top 10 or whatever the user asks me. Right. So I have created my constructor, and oh, this guy's still not happy. That's because maybe it's not chocolate. I don't know. Let's see. Oh, it's still not happy now. Does not declare because it's not marked static. Sorry, this is not C++, right? This is C#. So this is how we should do it. And we see capacity, and let's not call it. Yeah. Okay. So we created our max heap object as we were expected to. Our next task is to read the next element in the input list. So basically now, because we also know that, it's go to step 2. So essentially it is asking us to read one after the other element in the input list. And we, being very smart programmers, we know that it is essentially asking us to write a for loop. Yeah. So I say elements dot count. Okay. So I'm basically writing a for loop to iterate over my input list. Count gives me the total number of elements within the list. Yeah. So it is like if you're doing STL, if you work with C++ vectors, then it would be something like size. Huh? But let's not focus on that part. Yeah. The focus is our implementation of the algorithm. Okay. So let's not focus on the C# and versus C++ business. If we already have filled up the max heap, okay, how do I check this? So I need to obviously go to the max heap and say, you know, what is your count like? So we need to understand, you know, capacity is something different. Capacity 5 ho sakta hai, lekin count 0 ho sakta hai. So my max heap, for example, has the capacity to have 5 objects, but I have currently not put anything. So for example, when I'm starting, then the max heap is empty. So it has the capacity to fill in 5, but right now nothing is there. Yeah. So that is my current count. Understood? Do we understand that?
Yes, sir.
Yes, sir.
Yeah. So we want to check if we have already filled up. So we want to see if the count, okay. So max heap dot count, अभी नहीं है count, लेकिन हम assume करेंगे है. If it's equal, if it's not equal to, okay. So check if not, okay. So if not, then we have to insert, right? So if it is not equal to the count, okay, then we have to insert the element, right? Is everyone still with me?
Yes,
or
sir.
now you're dozing off?
Yes, sir.
Yes, sir.
Okay, perfect. Sounds good. Three people are at least alive and kicking. So insert the element. Yeah. So we need to be able to insert the element into the max. Okay. Again, there's no insert function. We have to obviously write all this. But right now we are just looking at the very top level of the algorithm. Yeah? So we say insert the element. What is my element? My element is nothing but elements I. Okay, so I have inserted as instructed on line 16. Yeah? So it is part of our third step. If not, then insert it. This is precisely what we've done. If yes, compare it. So that means you have reached the count. Yeah, so you have reached the capacity already. Okay, then we say else. So we should here say if count is, you know, basically saying if it's less than count, we want to insert 5. Yeah. Then we do that. Else, what should we do now? So we are now here in the yes part. We have hit the capacity. Then we are saying compare with the root element. So if can somebody fill me up? It's like just me writing the code here.
We can say that max heap dot get root for the getting the root.
Right. We say max heap dot say top. Okay. Or we can say root value. And what should we do? If it's what should we compare? So what should we compare it against? If it's greater than what?
Elements.
Elements I. Yeah. So एक काम करते हैं. We put this element I for simplicity. We put this element I. We say current element equals elements I.
Sir, it should be in for loop, I guess.
Right. I was just seeing who would tell me that. Right. Now, root value, and let's say instead of elements I, we writing elements I subject, we will now replace it with current element. Yeah, that becomes easier. So if it's greater than current element, so क्या करना चाहिए हमें?
Replace.
So root element is bigger. So we are here in this condition. Root element is bigger. Root element is bigger. Then what should I do? replace the root element of the max heap with the current element. So what should I do? I should say max heap dot replace. Again, we have to obviously do this. Replace root. Okay, so we are saying replace root with what? With the current element. Okay. And if not, if it's smaller, then we have to throw it away. So I basically don't have to handle this part. है ना?
Yes.
बस ये हो गया तो हो गया अपना algorithm. It's done. Last में we should just return max heap dot elements. So whatever is in the tree, we should return it. That's it, done. Is everyone convinced?
Yes, sir. Very much.
Okay.
Yes, sir.
Yes.
Obviously, there
Yes,
are a lot
sir.
of red here, है ना? 1, 2, 3, 4, 5. 5 red है. Okay. We need to obviously solve the red part. Huh? Nobody likes red. Yeah, even at the traffic light, we don't like red. So we should replace the red. Yeah. So what we do is we say we want to implement that. Okay. So we say create method this. Okay. We keep doing that. Obviously, we have to write the implementation. Okay. Perfect. Okay. Sub red chala gaya. But obviously, we haven't done a proper implementation. The moment we call this, it's going to throw us not implemented exception. So that's something we have to implement. Okay, so we will start with the simplest of them. Yeah, so we need to have a count, which means we need to keep track of how many elements have been. So first of all, we are going to keep track of these elements, now the elements that we are keeping in our data structure. We need to keep track of that. So we create a list to track those elements. Yeah. So we call it better property. So we say pop. We call it. It's what is it? Type is list of integer, and we are calling it elements. Okay. Don't worry about the elements. Is new list of integers, and we are going to give it the capacity. Okay. What's the issue? Members with the same name is already declared. We call it get elements. We don't need to. We can sort of get the element here. It's a property, not a. Okay. So we good. Now we need to give back a count. So count kya hoga? Jitna elements ka size hai, that is a count, right? So I would say return elements dot count. Are you all following me?
Yes,
Yes,
sir.
sir.
Yes, sir.
What we've done, we've basically done, we've created a list of integers that we want to keep track of these elements that I would be inserting into my data structure. So मुझे time पे तो रखना पड़ेगा उनको. तो मैंने एक list बना दिया जहाँ पे रखूंगा मैं. And then, count, जो हम count पूछ रहे हैं यहाँ पे, ये count क्या है? जितना elements अभी insert किया है already. Right? So the elements that I've already inserted is what the count is about, right? So that count is nothing but the count of this list, right now. So that is implemented now. Okay, now we this is also very simple. So let's first try to tackle this one. So tell me, what should I write here? I want to give the root value.
First element in the list.
Yeah, so I will say first element in the list. That does not work. Tell me exact. Now we're writing code.
Maximum of that max heap root heap top.
Tell me the exact things that I should be writing here. The computer will not understand your intentions.
Show attributes.
What were we supposed to be returning when I say return root value? For example, this is my current data structure state. And if I say get me root value, क्या value वापस आना चाहिए मेरे पास?
Element at index 1 0.
What value?
34.
34. Where is it? At what index it is in the list?
Index 0.
Right. So
element at index 0.
So elements at index 0. Then now we write, the interesting part. And if we write these two interesting parts, our job is done. Now I want real attention from your end. Okay, this is where the meaty stuff is. So how are we doing the insertion? Let's look at that. Okay, so for example, I'm going to insert 0 now. Yeah, because I ignored 55, but 0 needs to be inserted because 0 is less than the root value, which is 34. So I'm going to be inserting 0 into the list. Right? Sorry, no, we are not here. So that would be replaced. Yeah, insert kar rahe na abhi hum. So insert mein, we are just going to add something. Let's imagine that, we were top 6 actually. So I just want to demonstrate the insert case. So now 0 comes in and 0 would be added where? Where would 0 go? It would go
last.
Which position?
Left child of 2.
Where would it go?
Left child of 2.
Last. Okay. Then how are we going to now make sure? So we put the so there is always. Okay. So let's see. What is the position of 0 in this? Let's calculate. क्या है position 0 का position क्या है यहाँ पे? What is 0's position?
5.
5.
5. Yes. 0, 1, 2, 3, 4, 5. 5. Everybody can see this?
Yes.
You can see what I'm writing, right?
Can you zoom a little bit? Yes.
Okay. Can you see now?
Yes.
Yeah, perfect. Okay, good. Now 0's position is 5. What is its arrow other direction? Now what is its parent?
2.
Yeah, and how do you calculate that? So how do you know? So we are now talking of positions, yeah, so not value. Okay, so this is at 0th position. This is at 0th position. This is at 1 position.
Parent will be 2 plus 1.
3rd position. 4th position. And 5th position. These are not needed. Okay, so this is 1st position. 2nd position. I'm talking of with reference to the array. Yeah, so this tree is actually within an array, within a list. Okay, and we are talking when we say position, we are thinking of its position within the array, within the list. Okay, perfect. Okay, I should not be, this is not the links position, this is the nodes position. Nodes position. This is the nodes position. Okay, so it's all clear, right, to everyone here? Okay, now when I look at this, what is its parent?
Index minus 1 by 2.
Right. So if I look at 5 and you know, just for the sake of it, imagine there was another child here. Okay, so just imagine for the sake of it, there is another child here. Uska position kya hoga?
6.
6 hoga, right? So okay, uska position 6 hoga. And if I want to calculate the index of the parent of a certain node, okay, then we see that, you know, the children are always having consecutive node values, yeah, index values. For example, 3, 4, 5, 6, और आगे बढ़ेंगे तो 7, 8, 7 का होगा 9, 10, 5th का होगा 11, 12, 13, 14, and so on, right? So if you want to calculate the parent index, then somebody told me it's index minus 1 divided by 2. Yeah? So let's see how that formula is actually giving us the right values. Okay, so let's write the formula here. We're saying parent index equals child index minus 1 divided by 2. Huh? This is what you told now?
Yes.
Right. So if let's work this out. Yeah. Let's say the child index is 6. So what is 6 minus 1? 5. 5 by 2. What is 5 by 2?
2.5.
5 by 2 is
2.5.
5 by 2 is 1 by 2.
2.5. 2.5.
2.5, right? But we are not dealing, you know, there's nothing at 2.5 index. Yeah? Array mein se 1, 2, 3, 4 hi chalta hai.
We need to take
We
floors.
get the integral value of that, and 2.5 ka integral value kya hai? 2. So you know, this is a bit misleading. Don't look at this 2. It just happens ki wo 2 ka position pe 2 ka value bhi hai. I'm talking of this 2. Okay. 6 ka parent 2 hai by this formula, and yes, we can check that it is the case. Yes, so the formula is giving us right answer for the right child. Let's check it for the left child. Left child ka index kya hai? 5. 5 minus 1, 4. 4 by 2, 2. Sorry. Yeah. And you can sort of, you know, for your own satisfaction, you can verify with some other numbers also. For example, 6, then here will be 7 and 8. So let's see, 8 ka parent kya hona chahiye? 8 ka parent hona chahiye 3. So 8 minus 1, 7. 7 by 2, 3.5. Integral value 3. Yes. Okay. And it will work. So the parent index is child index minus 1 by 2. So now coming back to our problem statement, we inserted this at position 5. The 0th element was inserted at position 5. Now what is that we should be doing? Hello? Hello?
Hello.
Yeah, so what is that we should be doing now?
Inserting element.
Yeah, we already inserted. Yeah, so insert, for example, we can do that. You know that. So how should we insert? We should say elements dot add and the current element. So we added, so we inserted, wo yahan pe aa gaya 0. But what should we also do? Is this correct? Would that be good enough?
Compare it with the parent element.
No, so yeah, so the point is we should be now making sure that we are maintaining the
index.
property. Yeah, that's very essential. It is not just about insertion. Make sure that we maintain the heap property. Okay, and this is what is something that we should ensure. So how are we going to maintain the heap property? What are we going to do? What did we say? This is a max heap, right? So max heap में the parent node should be higher value than the child node. True?
Yes. Yes, sir.
Yep. Okay. So now what are we going to do? We are going to look at its parent node. How do we calculate the parent index? We say child index minus 1/2. So iska child index is 5. So we can get the child index of the last element that we introduced. And from that, we can find the parent index value. True? And once we found the parent index value, what do we do after that?
Compare.
Okay, yeah, we compared. Yeah, and then we realized key, 0, it is at its proper place. In this case, for example, let's say it wasn't 0, but it was something else. Instead of 0, it was, let's say, 59, 58. Okay. Then what happens? 58 gets compared with 2, and then what should you do?
Swap.
Swap the element. So swap करने पे क्या होता है?
2 will be the child node.
2 becomes the child node, and 58 becomes the parent node. And then what should you do?
Then again compare it to the parent.
Perfect. So we should keep doing this. Now the problem has just shifted from this node to this node, isn't it?
Yes.
Right. So then we treat this as a child node. अभी तक हम 5 बोल रहे थे, अभी हम 2 बोलेंगे, index 2. And then we will calculate its parent node. What will be its parent node? 2 minus 1/2. What is 2 minus 1? 1. 1/2 half. Half का integral value 0. So we reach the root. And then we do the same thing here, right? And then we swap it again because we realize that 58 is bigger. This is precisely what we want to implement here. So now who can help me that there? Come on, we just have to write these 2 functions and we're done. This turmoil will be over. Come on, quick. I think the session is for like 2 hours. So we got like half an hour. If you guys help me, we can finish this. See guys, the point is not that, I can, whether we're not testing whether I can write some code or not. Maybe I cannot, I don't know. Yeah. But that's not what we are here for. Okay. So what we are here for is basically to together learn something. Yeah. And if I am the one who is writing the code, then the learning is absolutely, I can ensure you it's almost 0. The only way I have learned in my life is when I did things myself. Yeah. So unless you tell me what code to write, you're not learning. Okay. So please help me out. We described the process now. Okay. So we have inserted the element at the very end. Now what should we do?
We'll get the last element.
So, say that again.
We'll get the last element, which will be integer temporary is equal to element dot size -1.
Okay, but we have the last element. It is this.
No, we'll get the index of the last element.
We get the index of the last element. Okay, so we say int index equals. What would be the index of the last element? It will be elements
dot size
count. It is a total number of elements minus 1.
Yes.
Okay, I got the index. Abhi kya karne ka?
Now we'll compare. We'll find the parent of this index.
Okay. So let's find the parent index. How do you calculate the parent index? I would like somebody else also to spin, please.
Index minus divided by 2.
Yeah, so let's call this the child index. अभी हमने formula लिखा ना वहाँ पे, right? So अभी हमने क्या लिखा है यहाँ पे? Child index minus 1/2. सभी को समझ में आया ना?
Yes, sir.
Yes, sir.
Right? Why do I not hear many voices? Yeah. I calculate the parent index. अभी क्या करने का?
Compare the value to both
Compare the
indexes.
value. So if condition लिखने का ना? So I say elements. Parent index
is greater
than the
it's, okay, let's write it the other way. So we say elements child index
lesser than the parent index
is greater than parent index. Okay, then what should I do?
Swap it.
Swap
it, isn't it? I would like to swap. Okay, and I would say swap what parent index with child index. Barabar? And we would have to obviously implement the swap function here. So we implement the swap function. So we say private void swap int index A index and int B index, and we say var temp equals
A index.
Elements. Yes, you're right, but we should say elements of A index. Okay, then we should give elements of A index the value, sorry, the value of element of
Index.
index. Yeah, very useful stuff, isn't it? And then we say elements
of B index.
Perfect. Element of B index equals the temp value. So we essentially swapped the two values. Okay, that's what we've done. Yeah, and we can sort of keep it at the very end because it's not a very interesting function. Yeah. So we keep it here because that's not what we are interested in. What we're interested in is these two really amazing functions that we want to write. So that's where we are going to use our brains. Yeah, so swap is done. And great, so swap is done. Yeah, so we swapped. Now what? But we know that we have to somehow keep going to the very top, isn't it? वो जो 58 था, 58 ने जर्नी यहाँ से चालू किया था, फिर यहाँ पे आया, फिर यहाँ पे गया, और अगर ये ट्री बहुत बड़ा होता तो और भी ऊपर ऊपर जाता. So what should we do? Obviously, this is only swapping these two elements, है ना? But we want to keep going, na? So yes, we should obviously do something.
For loop.
Yes, for loop, while loop, something like this, huh? Okay.
Yes.
So we say while. What is the breaking condition? When should we stop?
Child index is equal to 0. Parent.
So parent index is 0. I cannot stop because the moment parent index is 0, I might still want to swap 50.
The child index is equal to 0.
Let's see here again. Yeah. So I think 58 started here. Huh? 5 ka bana. So it's a pain. We need some platform where explaining algorithm becomes easier. Okay, so what? It hates me. Okay. So 5. Child index is 5. Okay. Then what was parent index that we calculated? Parent index was 5 minus 1/2. Okay. So okay. Not 4, 2. Okay, and then now child index becomes, parent index becomes, what does parent index become fast?
0.
Perfect. 2 minus 1/2, 0. Now, should I stop at this point?
Now we'll compare.
No, because I want to swap. Now I want to swap this parent index. But after that, what happens is, so now my child index becomes 0. Now my child index is gonna become 0. What does my parent index become at that point? 0 minus 1 by 2. What is 0 minus 1?
-1.
When we will going to complete, sir? I think the session is for 2 hours now. 10. Oh, it's already 2.5. Huh? I didn't realize that. Oh, this I was thinking we are, at 12:30, but it looks like it's already 1. Okay, so do you have something preceding this, guys?
No, sir.
No.
No, sir.
Would it be okay if we go on for like another 25 minutes?
Yes, sir.
Try to finish this off, or I'm okay if you guys say we shouldn't. We can stop here. It would be a shame, we didn't complete it, but you guys can take that as an exercise. So if you are dying to go out of the session and hot food is waiting, then I have no problem. We can stop.
Oh, sir, we'll
Complete quickly.
We can complete it.
So
I need to see at least say at least 15 yeses on the chat box. If not, then I think we should stop.
Continue, sir.
Continue, sir.
Yeah,
Con-
but
so
I
please
hear
continue.
Okay, that is a good response. Okay, fine, great. Okay, that's enough. Thank you, guys. Okay, but I don't want to enforce anything. Yeah, so in case if you're not interested, then we should stop. But looks like that's not the case. Yeah, so thanks. Okay, so what is the parent index going to be?
Negative value.
Negative 0.5. But we take the integral value. So what is negative 0.5 integral value?
-1.
No, it is 0. Again.
0 only.
0.
Okay, so you see that the parent index is 0 again. So now next time child index is 0, parent index is 0, child index is 0, parent index is 0. ये चलता रहेगा जिंदगी भर. So what is the breaking condition? The breaking condition is when these two indexes become
0.
no, they become
Not equal to 0.
they become same. If I tell you that the parent index and the child index is the same, then you should say there is no point swapping. We should stop.
Yes.
Right. So if they become same, then we stop. Simple. It's very, it's very common sense stuff. You can actually now take the session, look at it back, and see whether you can explain to a 12 standard guy or not. I think you will be able to. Because there's now rocket science stuff that we did here. Okay, now the last bit that we should take care. Obviously, we swapped, great, that's nice. But we should also update the values of parent and child, like I was doing in the text box there. I was constantly updating the values of child and parent, right? Otherwise, we run into an infinite loop. So child index becomes the parent index, and parent index is calculated again based on the new child index. Will this work? I think it will.
Yes.
Yes, sir.
Yeah, so we have made sure that our heap property is satisfied all the time, isn't it? The only thing, last thing, yeah, is where is the last thing? Yeah. Okay, now replace root. Okay, so we'll come into a completely different thing now. Okay, so we are at replace root. Let's say we are looking at how many values? Yeah, okay. ये insert वाला case अभी निकाल देते हैं. And let's say 2 comes in. Okay. So 0 comes in. Okay. So I was at 50. Let's say 55 was at the top here. Okay, and now the value of 0 comes in. I'm not talking about the index 0, I'm talking about value of 0. Okay, so the value of 0 comes in and we check with 55. And we say, okay, clearly 55, you need to go out because I change all this back to our original case. I was looking only, I'm interested in only 5 elements and 5 are only filled. So 55, you need to go out. Okay. So I'm going to take 55 out and I'm going to put 0 here. Okay. So what is the first thing we're going to do? We are saying replace root. That means we should throw away the top element, isn't it? So what should we do at this point? Element?
Compare it.
No,
Compare.
वो comparison वाला case तो बाहर हो गया. यहाँ पे compare किया हमने. अभी हमने decide कर लिया. We want to replace. वो decision हो गया. I'm telling you to replace root. There is no comparison. Yeah, I am asking you. You should replace the root. So the element 0 becomes the current element. So we inserted 0 here. Okay, but we also need to make sure that, what should we make sure?
If property is satisfied.
Exactly. Yeah, we need to make sure that the heap property is satisfied. Okay. So how do we make sure that?
Compare with the child.
So what are we going to do now? Let's just come here. So you see that, you know, the last exercise हमने किया insert वाला, we were sort of going from bottom to top. Swap to करना ही है. But we were going from like bottom to top. We started from here somewhere, then यहाँ पे आए, then यहाँ पे आए, and then we stopped. Now in this case, what is going to happen? We are starting at the
top to bottom.
We are starting at the top, and we want to make sure that, for example, if it's 0, you know, 0 should really go down, yeah, because it is definitely not the max element, and we have other elements which are maximum. Okay, so 0 should really go down. Okay, so what do we want to do? We want to now look at the
child nodes.
We want to look at the child nodes. Yeah, and then we want to calculate one of the child nodes, its parent node, and the parent node needs to take the value of the child node. And then we need to keep doing this like we were keep doing in the last example where we were keep going up. We need to keep going down.
Down.
Yeah.
We will replace with 2i plus 1.
Yeah, so we don't know now. We need to look at which child position we need to go at. For example, sorry. Right, so we need to look at both the child nodes, and then we need to check which one we should really get to the top, isn't it? Because, for example, in this case, we have 3 and 34. Which one we will take to the top?
34.
34, right? So we need to check both the values, na? Right? करके फायदा नहीं है ना. अभी, for example, 34 यहाँ पे होता तो ये 38 मान लो, तो right? So ये 38 ऊपर जाना चाहिए ना?
Yes, sir.
So I have to check both the values and then do it, na? So let's do that fast. Yeah? So अभी जैसे हमने यहाँ पे build किया था ना? Now I have the parent node. I need to calculate indexes of the child node. So how will you calculate the index of the child node? So if say my parent index is 0, how do I get the child index? You can see here. I can do 2 times parent index and then add 1. I'll get child index. Yeah. So if you were to write the other formula, that would be
2 into parent index.
Yes, child index equals 2 times parent index
plus
1. But इससे तो मेरे को एक ही child index मिलेगा.
Plus 2.
Plus 2 for the right child.
So this gives me the left hand side node, right? 2 times parent index. So 2 times 0 plus 1, I get this. And then this is left child index, right? Is everyone with me?
Yes, sir.
Yes, sir.
This is left child index. Okay, how will I get the right child index? I need to add 1 more to it.
Yes, sir.
Yes, sir. Right.
Right child index.
So upon
plus 1.
Plus 2.
A plus 1 other. This was plus 1 and we are adding 1 more to it. So we get
Yes,
plus,
yes.
right? So this is basically what we write here. We say left child index equals 2 times. So let's call the parent index in this case. You know, we are starting at the top. Yeah? So parent index is 0. Okay. So we say parent index plus 1. And what would be the right child? It will be plus 2. Perfect. And now what should we do? So, okay, I've got the two nodes now. I have these two nodes now. Okay, what should I do? I should compare the value
Compare
of the
with
parent
root.
with each of these childs. That's very important. Okay, so we need to sort of maintain the largest child, the largest index, the largest element index. Yeah, because we don't know whether, for example, it's quite possible that, we have three things that we are looking at. We are looking at the root node itself, because the root node itself can be 100, for example. So either we are looking at the root node and we are looking at the two child nodes, and then we are deciding which one should really come to the root node. Yeah. So maybe the root node needs to stay where it is, then there is nothing to be done. Or the root node needs to travel to one of these childs. Okay, and now which child? So we have three nodes in which we are doing sort of a comparison, and we are trying to find out which one should really come to the top position. Everyone getting that?
Yes, sir.
Right. So we maintain a largest element index, and what do we say? We compare the values. So for example, let's say the largest element index to start with, I initialize it to the parent index. So I say, okay, largest element index is the parent index. And then I'll compare with the two childs and I'll appropriately change it. Okay. So I say largest element index equals left child. Okay, we should compare first. So elements left child index. Okay, another important piece. Okay, we'll come to that later. Elements left child index, let's say greater than elements largest index. If that is true, yeah, if the left child index is greater than the value at the largest element index, then my largest element index should become my left child index. Na? Are you guys following this, or is now going over the head?
Yes, sir.
Following it, right?
Yes, sir.
All I'm doing is I'm comparing the two child nodes values, and then I'm keeping track of that in an index called the largest element index. Yeah. Okay, so now after this point, my largest element index would either point to this or this or this. Yeah. What if it is pointing? So when should I do the swap operation? Swap operation kabhi karna chahiye? If my largest element index is, let's say I introduce 0 here. So I initialize my largest element index to the position 0. Okay, this is where I started. Then I compare the value. Okay, let's make it confusing. Okay, so I compare the so my parent index, where I'm starting is at the root position. Yeah, this is where I have replaced the value. So I'm putting it at 0th location. Then I say, okay, that is my largest index. Okay, then I compare the value of 1 with 38, and if 38 is bigger, okay, if 38 is bigger, left child index ka value zyada hai, then I say largest element index 0 nahi hai, sorry, it is 1. Okay, then I say अगर right child index का current largest से ज्यादा है, so in this case कम है, लेकिन मान लो ज्यादा होता है 39. So then I compare the value of elements right child index, which is nothing but 39, and I compare it with the elements largest element index. Now largest element index is not 0 anymore, it is 1. Yeah, after this point. So I'm comparing 39 with 38, and 39 turns out to be bigger. Then my largest element index becomes right child index. इतना समझ में आया?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Now, having done that, how should I decide whether I should swap or not?
If largest index not equal to parent index, then swap.
Perfect. If the largest element index is not equal to my parent index, yeah, because if let's say we introduced 100 instead of 1, then my largest element index would always be 0. Yeah, and in that case, there's no point of swapping. The tree is already hippified. Yeah, कुछ करने का जरूरत ही नहीं है. So that's our breaking condition. Okay, so we break, if that is not happening, okay, then we basically do nothing. That means we break. Yeah. So what should we do here? Now we should swap. True? We should swap now?
Yes.
So we should swap the parent index with the largest element index. I mean the values corresponding to these indices, yeah, not the index. We're not swapping the indices, we're swapping the values at that point. Okay. And then we should do what should we do? We should update. Now we need to, for example, the यहाँ पे 0 था. Okay. 0 may forget, let's make it 2. Okay. And let's say this is 35. So यहाँ पे 2 था. यहाँ पे 38 and 35 है. So this became our largest element. Then we did the swapping. So 38 moved here and 2 went down. Now is it hippified in this subtree? Is everything okay?
No.
No.
No, it is not, right?
Yes.
Yeah, who says yes? It is not, right? So we need to swap 8 and 2, yeah, because 8 is clearly larger. So we need to basically repeat the entire process that we've done again. And what is going to be our stopping point?
Length of the array.
The stopping point is when we hit this,
largest
condition, right? So the stopping point is when the largest element index happens to be your parent index. At that point, you basically stop because that subtree is hippified already. Yeah. So we say, exactly what we did last time. We introduce a while loop now. Yeah. So we say while. Yeah. So in this case, because
it will be max, means element equal to maximum length of list. It will be maximum length, means last. No.
Yeah, so basically we say, while the parent index is
length
less than equal to less than count, we can say, right?
Element.count.
So till that point we can go on basically.
Yes.
Okay. And we need to, now we swap the elements, we need to update the positions, right? Like, for example, if you remember what we did in the insert case, we would like to swap the positions. Yeah. So we say parent's index. So parent index becomes the largest element index. True?
Yes, sir.
True. Yeah. And we should put this in here. We should update that now. We should update our left and right child indices. Okay, so parent index becomes the largest element index, and then we can basically continue. True? Is everyone getting this?
Yes, sir.
Yes.
And this can be actually here. There's no problem in this. Here. We can initialize this every time to parent index, and we can start. And if we make a swap, right, we swap the parent index with the largest element index, and then we continue doing this till we hit this. Yeah. Actually, at this point, we can break. If this happens, then we can even break here because we know that there's no point going down, down, down. You see, because parent index is not changing after that point. Yeah, we change the parent index only when we swap. Yeah, so if we haven't swapped, that means there's nothing to be done. That means we break. Following, everyone?
Yes, sir.
Yes, sir.
Okay. And I realize that even this can be brought in because I don't need that. All that I need is that. Okay. Right. So there is one more thing that we haven't really handled, which is the calculation of this large left child index. So imagine that you are here. Your parent index is this position, yeah, and you now calculate the child indices. Now the child indices turn out to be this and this, but there are no nodes at that point. So the moment you try to do this, it's going to crash. Do you get me?
Yes, sir. We have to write one if condition for that.
Exactly. So we have to put an if condition here, and we have to say child left, if left child index is less than elements dot count, then only should I do this thing. Otherwise, it will lead to a crash. And this also I should do if right child index is less than elements dot count. Then I should do this comparison. Otherwise, the comparison makes no sense. Now I think it's complete. Okay. Who is excited? काम करेगा नहीं करेगा? There's a lot that I wanted to sort of cover. You know, for example, I wanted to show that in here. Okay, let's come to that point first. Okay, so what we are going to do, we are going to create this is the nearest neighbors algorithm. To make it a bit simple, what we do is we declare this as public static so that we can call it directly without having to create an object. We also make this class public so it becomes easier to access it. And then we say nearest neighbors, okay, dot get nearest neighbors. Okay, we need to provide a list of elements. So first, let's build up a list of elements. We say elements equals new list. Let's initialize the list here. 22, 4, 5, 6. Some interesting numbers: 5, 10, 19, 23. Okay, should be enough. Okay, how many are there? 3, 6, 7. 10 कर लेते हैं. 44, 0, and 29. Okay, that's 10. And let's say we want only the top 3 out of these 10. Huh? Now imagine, you know, typically you would be writing this where the data is really, really huge. You know, so we're looking at, you know, 100,000 elements kind of thing. So you know, try to sort of scale that in your head. Yeah. And I would be looking for like top 50, for example, you know, what I can display in one page on a website, for example, you know, like Google has so many results, you always go on the first page. You never go past the first page. Yeah? So I'd be displaying 20 at a time, for example. Yeah? In this case, we'll make it simpler. Out of 10, we choose 3. Okay. So what is that I need to send? I need to send it the elements, first of all. And I need to tell it the count. So in this case, I'm interested in 3. So I'm just saying, you know, give me the top 3. Okay. We try running it. Let's see. You know, it's going to give me something back, isn't it?
Yes.
Say top 3 equals this, and then we need to say write a print list kind of function to which I can give this top 3. Actually, you should say result. That's easier. Okay, so we write another function here. We call it static void print list, which takes nothing but a list of integers. Okay, and what we're doing is we essentially write over follow, do iterate over it, and Okay, sorry guys, I had to sort of, this is not the interesting bit. We're just printing a list. Yeah. So let's see what's happening here. Run this. Oh, what happened? Let's do control F5 so we can actually see for ourselves what happened. So we got 0, 4, and 5. Does it live to our expectation?
Yes, sir.
Hey, first time right. Yeah. That's a good achievement, isn't it? Together we could solve this problem and we got it right the very first time we hit it. No problem.
Yes, sir.
Yeah. If I had time, I would have shown you how the elements are traveling up one by one. We could have printed the intermediate results and then we would have seen it for ourselves. I also wanted to show you how in the tree it looks so you can really visualize for yourself how things are moving. So I just tried doing my best with this website, but it's obviously not the same. I'm sorry, we couldn't cover all of that because it's not a small topic. I need to first tell you what the problem statement is, and you also need to hear from your end what you would do in such a case, and then slowly introduce you to the data structure, the algorithm we write, and then we actually implement. That's, I think, a big thing to be done in a short amount of time. If regular class, I would have taken at least 2 sessions to do something like this. But I'm hoping that, whatever we did, you could learn something out of it. And maybe it's time we should, maybe, the few questions, if somebody has some questions, I'm very well, ready to take some questions. Klingenberg is hiring, that's my shameful advertisement. We are hiring, I'm looking for really good people. Yes. Okay, so.
Hello, sir.
Yes, yes.
Sir, can we use insertion sort for maintaining that heap property every time? We are swapping element every time. So if we use insertion sort for inserting, it will reduce all the efforts required for maintaining that heap condition.
And tell me, what is insertion sort? What does it do?
I will pick first 5 distances and sort. I will sort it using insertion sort.
The first 5.
Yes, sir. Then the last element will be higher. So next element, if next element is less than the last element, then it will be overwritten at last position. And if we call insertion sort, it will be sorted in just one swapping. So the efforts required for maintaining heap condition will not be required.
So when let's say you are maintaining this list, which is you are saying that it would be in a sorted state, right?
Yes, sir.
And then a new element comes in.
Yes, sir.
Okay. Now, when this new element comes in, how are you going to insert it to its rightful place?
Because, sir, the array is already sorted. So the comparison will be with the last element of the array.
Yeah, but you don't know its proper place, na? Uska proper place dhundna padega, na?
Yes, sir. So insertion sort will work that.
Yeah, it will work. But I'm asking you. So how will you put the element in its proper place? That means what will you do?
So I will find smallest index from 5.
We're not talking about indexes anymore. You're saying you have a sorted array with you, huh? With,
yes, sir.
Let's say 10 elements. Okay. Yes. And now 11th element comes in.
Yes, sir.
And you realize कि okay, मेरा bucket तो full हो गया है. इसमें से एक को निकलना पड़ेगा. अब किसको निकालोगे आप?
Sir, I will replace with the last element first.
This case, right? So if you decide that somebody needs to go, it's going to be the last element.
Yes, sir.
But the element that we are talking about, जो अभी अंदर जाने वाला है bucket के अंदर, उसको आप कहाँ पे डालोगे?
Sir, we require to sort the array again. So, but sir, sorting will require only one swap because all the other elements are sorted. So the only one swap is required for sorting.
No. So let's try and understand. It's not one swap. You are maintaining a sorted array. Okay. You decided that the last value should go. Okay.
Yes, sir.
But the value that is coming in is not necessarily coming at the last position. So first
Yes,
of
sir.
all, you need to find it the rightful place for that element.
Yes, sir.
What kind of an algorithm will you use for that? You need
Selection
to,
sort for that.
but
Selection sort works for.
No, that's okay. We should. The namings are not important. So
Okay,
let's look at what you would be doing. You would be going over every element in the array, and you would be trying to find the rightful place for this new element.
Yes, sir.
And let's say that comes bang in the middle of all elements.
Yes, sir.
Which means now we're not talking of swapping, because you're not going to swap. You need to shift the elements. Imagine
Yes,
that
sir.
there are 5 people standing in a row as per their heights. And now there's one guy who comes in who fits right into the middle of these 5 elements, 5 students. Shouldn't
Yes,
the
sir.
other students shift?
3 and 5 will be.
It's not a matter of a single swap. Every element needs to shift.
Okay. Yes, sir. Yes, sir.
Yes?
Yes, sir. Got it, sir.
So not only that, it has a problem with the shift, because shifting is really bad. That means, you're actually doing a lot of swapping, one. And second, the algorithm itself is very time taking, because you are going to be sorting every single time this list, because in order to find my rightful place within that list, you need to scan the entire list. If you look at what we've done with the tree, why the tree is essentially here, and this is the kind of thing we should be talking about, but time does not permit that. So why we look at the tree structure? The tree structure, if you see, imagine this, this is a full tree with nodes here. I'm just dragging things now because I don't want to create new nodes. It takes a hell lot of time. But imagine that this is the entire tree, and I push one element here. How many total swaps would I have to go through? So let's say I'm introducing -100 here. How many total swaps would I have to go through?
2
at
times.
max 1 swap here, and at max 1 swap here.
Yes, sir.
So what is the length of this? What is the total length of this? It is log n. If I'm looking at 100,000 elements, उसका total length, जो total swaps होगा, वो 10 या 30 के ऊपर ज़्यादा नहीं जाएगा. And if we are, so that's very essential that, even, so sorry, 100,000, we are talking of 50. So let's say I was maintaining a list of 100. Every time I would be making 100 scans, or at least on an average 50 scans to find my rightful place. And then I would be shifting on an average 50 elements. In this case, we would be shifting log of 50. And log of 50 is what? 5 elements. And the time is also corresponding. So I'm not scanning on an average 25 elements, and I'm not shifting 25 elements. You understand?
Yes, sir. Thank you.
Okay.
Hello, sir.
Any other questions?
Yes, sir. I want to ask that where can we find such questions like related to data structures?
I
like
don't know.
Practice?
I don't know really, because I did not find it anywhere. I'm pretty sure there's a lot of websites, so I think maybe this question was relevant when I was doing my third year of maths. That time resources were sparse. We had to rely on books in our hands. But अभी तो आप एक search मारो 25 result आते हैं. So I'm pretty sure there will be a lot of content on the website. Oh, there's one thing that I wanted to show actually. So that's a good question. Kila, is it? Right.
Yes, sir.
If you want to learn this, right? I mean, this is a nice thing, which really shows you how the heap works. Yeah. So for example, अभी ये heap बना हुआ है 0, 7, 14 और 12 के साथ. अभी हम इसमें insert करते हैं 100. और ये min heap है, मतलब minimum element ऊपर आएगा. सॉरी हम इंसर्ट करें ना, तो हम मिनिमम एलिमेंट इंसर्ट करते हैं, इसमें 5 इंसर्ट करते हैं. ठीक है. तो सी 5 केम हियर. अभी देखो 5 ट्रैवल करेगा ऊपर. हाँ, और यही हमने भी किया.
हाँ सर.
हमने ये बॉटम अप किया ना, तो ये हम दिस इज व्हाट आई वांटेड टू शो. हम एवरी स्टेप पे वो लिस्ट को प्रिंट करके दिखाते हैं. but we don't have the time to do that now. And then, let's say I introduce another element called 23. So because there's a min here, 23 comes here, and the property is already satisfied. So kuch karne ka zarurat nahi hai. Then I introduce, say something like 2. 2. Yes, let's see. So 2 comes here. Then it gets exchanged with this. Then it gets exchanged with that. And this is precisely what we did. We did with max, this is min.
Yes.
So maybe this is one good website, Kedar, where you can go. They have, I also did a search today morning, because I wanted to show some graphics, and therefore, so I also just searched it. It's not like, I knew this, but, so I'm saying you can basically make similar searches, and I think you would end up on some good, really good stuff. So then I looked at, what all they have, and they have some really good, so I was typically interested in, because I wanted to do this remote section. So I was thinking, how would I be able to explain heap and all the transfer and all that. And therefore, I was looking for something which can visually show you guys that stuff. So you can see, this is nice. So if you want to understand, for example, what's happening here, you can do it with a bit of visualization. Yeah. And I think that would be cool. Yeah. So I think when you see something, it sticks in your head. Yeah. It also forces you to think. So maybe this is a good website. Yeah. So this is something you can use.
Okay, sir.
I can share in the chat box if that helps. I'm going to share everyone in the meeting. Yeah. Okay.
Okay, sir. Thank you, sir. Sir, and one more question. So how do we approach such questions for the first time? Like in the first attempt, we went for the sorting, and then we realized that this is not the correct, and then
I would say that's the perfect approach. So you should always go with whatever your hunch is. So typically I always approach problems with the brute force approach, and then I always question myself if I have done an optimal thing. And these are this is precisely what you would do if you get into a really good algorithmic sort of job. And then the expectation would be that from your end you question your own solution and you say, have I done the best? And then you realize, okay, this is taking a hell lot of time, and I'm getting 10 results back. Clearly, there's something better I can do about it, right? And that's when you try to sort of think of what is an optimal way of solving this problem at hand. Okay. Obviously, you need to have some good understanding of the data structures that are being taught to you, so you can sort of relate to them. Okay. So I would say the approach that we started with, it was perfect. We started with sort. Somebody saying we should do a sort. And that would have solved the problem, yeah. But clearly it was a suboptimal solution, because it was going to take a hell lot of time, a hell lot of memory. And there are other aspects I did not touch on. For example, I wanted to show you how this works with a generator. So the idea is that, the numbers are coming on the fly. You don't really have them stored anywhere. Yeah? So a list of elements page, we will not set that list. We will send a generator, which will only give you when you ask for it. So there is no elements. Yeah? We are only generating. That nicely replicates what happens in real life. Because in real life, nobody would be reading 100,000 elements out of a database. That would be crazy. But then you realize that why certain data structures really make sense. Because if I'm going with a sorting needs all the elements in the main memory. And that would be an absolute fail approach. Yeah. So, I don't think there's a perfect answer, and maybe I'm just beating around. But the way I have always done it, and the way it has always worked for me, is I never get satisfied with what I do. So I typically, do it one way, and then I'm always looking for how can I better this. I'm really generally not happening with even when I get really fast at times, I'm still not happy, and that always keeps me on this edge to find out an even optimal solution to things. So I think. It's a very sort of philosophical answer, but that's what has worked on in my life. I'm never happy with my timings. So that always keeps me on the edge.
Okay, sir. Thank you, sir.
Okay, so thanks for this wonderful participation. I really appreciate everyone sticking out for so long. I know all of you are hungry, and I'm giving you philosophical lectures. I should stop this. Yeah, even myself, I'm very hungry. So thanks everyone. Thanks for joining. Thanks to the entire CDAC team for providing this opportunity. And I really hope to maybe do these sessions again. Yeah. So thanks. Have a great time.
Thank you, sir. Thank you, Kapil sir, for this wonderful session.
Yeah, it's my pleasure. Okay, I think this recording was going on, right? So, Keshav, if you can share that recording with me, that would be great.
Yes, yes.
Okay, cheers. Thanks, everyone. And best of luck to your, I think you're finishing your course. So best of luck for your interviews. And I'm pretty sure that,